Okay, so today I want to try out the Lean programming language slash theorem prover. And full disclosure, this is my first YouTube video, so it might be kind of bad. But yeah, I thought it would be interesting to go to learn here and try to read this book, Functional Programming in Lean. And so I don't have any deep knowledge of functional programming. I learned a bit of Haskell back in the day at university, but otherwise in my day job I don't use functional programming at all. And actually I want to get into like the theorem proving part with Lean because I want to learn more about mathematics, but since I'm a programmer, I thought it would be easiest to start with the functional programming part. And yeah, the reason I'm recording it is I thought it would be interesting to just see more book content on YouTube, like not just reviewing books, but actually just like going through a book and reading it and maybe going through the exercises. So yeah, that's what I'm gonna try to do. So if we go to the introduction here, I'm gonna make it a bit bigger. Maybe this is big enough. So Lean is an interactive theorem prover based on dependent type theory. Originally developed at Microsoft Research, development now takes place at the Lean FRO. Dependent type theory unites the worlds of programs and proofs. Thus Lean is also a programming language. Lean takes its dual nature seriously, and it is designed to be suitable for use as a general-purpose programming language. Lean is even implemented in itself. So the compiler is bootstrapped. That's actually cool. This book is about writing programs in Lean. When viewed as a programming language, Lean is a strict, pure functional language with dependent types. And that's actually interesting because one of the things that people always say about Haskell is that the fact that it's not strict, it's lazy evaluation is actually good for proving facts about programs because you can just do like substitution. You can substitute like function definitions or variable definitions wherever it's used, and it won't really change the behavior. And I always thought that that has something to do with with Haskell being lazy, and also you can like sort of define your own like control flow and stuff. Yeah, but interesting to see that they are going with a strict language here. But again, I'm not deep into functional programming, so not like I know a lot about it yet. A large part of learning to program with Lean consists of learning how each of these attributes affects the way programs are written and how to think like a functional programmer. Strictness means that function calls in Lean work similarly to the way they do in most languages. The arguments are fully computed before the function's body begins running. Yeah, which means you couldn't, for example, define something like if-else as a pure, like as a normal function, because like if you say if x is not equal to 0, return 42 divided by x, well, if you always evaluate that then part, like 42 divided by x, even if x is 0, then the program would like crash, right? And if it's lazy, then you can do that, what I was talking about earlier. Purity means that Lean programs cannot have side effects such as modifying locations in memory, sending emails, or deleting files without the program's type saying so. Yeah, that's actually really cool. So it's probably gonna be something like Haskell's monads. Lean is a functional language in the sense that functions are first-class values like any other, and that the execution model is inspired by the evaluation of mathematical expressions. Dependent types, which are the most unusual feature of Lean, make types into a first-class part of a language, allowing types to contain programs and programs to compute types. That sounds interesting. This book is intended for programmers who want to learn Lean, but who have not necessarily used a functional programming language before. Yeah. Familiarity with functional languages such as Haskell, OCaml, or F# is not required. Good, because I'm not very good at Haskell. On the other hand, this book does assume knowledge of concepts like loops, functions, and data structures that are common to most programming languages. While this book is intended to be a good first book on functional programming, it is not a good first book on programming in general. Yeah, didn't expect that. Yeah, so the next paragraph says, well, it might also be interesting for mathematicians, and that we should read the book in order. So I can skip the getting Lean part because I already installed it, typographical conventions. Yeah, I think this is kind of self-explanatory. And yeah, that's actually kind of interesting that idiomatic Lean code makes use of a variety of Unicode characters that are not part of ASCII. So most programming languages, yeah, you're gonna have like all the function names and identifiers and whatever be using ASCII, if not because it's enforced, then just because it's a convention. I mean, for example, I know that in Go you can use Unicode characters for names, I think also in Python or in Rust, but yeah, usually people use ASCII. But I guess since Lean is so heavily used in math, yeah, people want to use alpha and beta and other Greek letters and like arrows and stuff like that. Okay, this is the release history. The book is licensed under a Creative Commons attribution license. So I guess by highlighting and showing the author here and writing it in the video description, I'm allowed to use it like that. So thank you very much for publishing the book under Creative Commons. I'm gonna skip over the acknowledgements, getting to know Lean. According to tradition, a programming language should be introduced by compiling and running a program that displays Hello World on the console. This simple program ensures that the language tooling is installed correctly and the programmer is able to run the compiled code. Since the 1970s, however, programming has changed. Today, compilers are typically integrated into text editors and programming environments, and the programming environment offers feedback as the program is written. Lean is no exception. It implements an extended version of the language server protocol that allows it to communicate with a text editor and provide feedback as the user types. Languages as varied as Python, Haskell, and JavaScript offer a real read-eval print loop REPL, also known as an interactive top-level or browser console in which expressions or statements can be entered. The language then computes and displays the result of the user's input. Lean, on the other hand, integrates these features into the interaction with the editor, providing commands that cause the text editor to display feedback integrated into the program text itself. Yeah, so that's really kind of different from the normal way you work with an interpreted language. That's kind of interesting. This chapter provides a short introduction to interacting with Lean in an editor, while Hello World describes how to use Lean traditionally from the command line in batch mode. It's best to read this book with Lean open in your text editor. That's what I'm gonna do. Let's see how to evaluate expressions. The most important thing to understand as a programmer learning Lean is how evaluation works. Evaluation is the process of finding the value of an expression just as one does in arithmetic. For instance, the value of 15 minus 6 is 9 and the value of 2 times 3 plus 1 is 8. To find the value of the latter expression, 3 plus 1 is first replaced by 4, yielding 2 times 4, which itself can be reduced to 8. Sometimes mathematical expressions contain variables. The value of x plus 1 cannot be computed until we know what the value of x is. In Lean, programs are first and foremost expressions, and the primary way to think about computation is as evaluating expressions to find their values. Yeah, so I guess it's an expression-based language, which I think is also true for Haskell and for Rust. Most programming languages are imperative, where a program consists of a series of statements that should be carried out in order to find the program's result. Programs have access to mutable memory, so that the value referred to by a single variable can change over time. In addition to mutable state, programs may have other side effects, such as deleting files, making outgoing network connections, throwing or catching exceptions, and reading data from a database. Side effects is essentially a catch-all term for describing things that may happen in a program that don't follow the model of evaluating mathematical expressions. Yeah, that's an interesting definition of side effects, but yeah. In Lean, however, programs work the same way as mathematical expressions. Once given a value, variables cannot be reassigned. Yeah, so I guess there's no mutable state. Evaluating an expression cannot have side effects. If two expressions have the same value, then replacing one with the other will not cause the program to compute different results. Okay, so I guess you can have this kind of referential transparency that Haskell has without having the laziness. This does not mean that Lean cannot be used to write Hello World to the console, but performing I/O is not a core part of the experience of using Lean in the same way. Yeah. Thus, This chapter focuses on how to evaluate expressions interactively with Lean, while the next chapter describes how to write, compile, and run the Hello World program. To ask Lean to evaluate an expression, write #eval before it in your editor, which will then report the result back. Typically, the result is found by putting the cursor or mouse pointer over eval. For instance, yeah, eval 1 plus 2. And this is actually really cool. We can do this right here, but yeah, let's try also in VS Code. So I created a project here with the Lean extension. It actually gave me Hello World by default. Let's say eval, actually can be eval main. It's kind of interesting that, so I guess it's evaluating main here, but I mean, this is a program that has side effects because we can see it's using the IO monad or type or whatever. I would be interesting to see that if we write a main program that, for example, deletes the file itself or something, and then we write #eval, if it actually carries out those side effects, or if it is has some safety mechanism to only use like benign side effects, like printing to the console. Let's see, 5 plus 5, and then we get 10. Interesting. And if I do 5 plus x, I guess I get an error. And I guess I can, it's a question, can I use what Copilot suggests, can define x like that? Even if I define the type, I would still get, I guess this is required that I write the value here. And yeah, works as expected. Okay, back to the book. Yeah, so it obviously has like all the normal rules of arithmetic. While both ordinary mathematical notation and the majority of programming languages use parentheses, for example f open parentheses x closing parentheses, to apply a function to its arguments, Lean simply writes the function next to its arguments, for example f space x. Function application is one of the most common operations, so it pays to keep it concise. Rather than writing, well, yeah, we have here an example where we're using parentheses to call string.append, and they have an example next to it without the parentheses, which, I mean, yeah, arguably looks a lot cleaner. Yeah, and it's really cool that it gives you the value right in the book. Would be even cooler if it was like running in the browser in some like WASM engine or something, and we could actually edit this and play around with it. I don't think that's possible here. Just as the order of operations rule for arithmetic demand parentheses in the expression 1 plus 2 times 5, where if you want 1 plus 2 evaluated first, parentheses are also necessary when a function's argument is to be computed via another function call. Yeah, so there's an example here, which actually is kind of weird because append is associative, right? So it doesn't really make a huge difference if you append like grade to oak or first or oak to tree first, but anyway, because otherwise the second string.append would be interpreted as an argument to the first rather than as a function being passed oak and tree as arguments. The value of the inner string.append call must be found first, after which it can be appended to grade, yielding the final value grade oak tree. Wonder if this is a reference to Java, because I think Java was originally supposed to be called oak. Imperative languages often have two kinds of conditional. A conditional statement that determines which instructions to carry out based on a Boolean value, and a conditional expression that determines which of the two expressions to be evaluated based on a Boolean value. Yeah, for instance, in C++, the conditional statement is written using if and else, while the conditional expression is written with a ternary operation in which question mark and colon separate the condition from the branches. Yeah, so that's actually, I think, because C++ is mainly like statement oriented, but for example in Rust, if and else, the normal syntax is just an expression. So you can use it anywhere where an expression is expected, like the question mark operator in C++. So yeah, I think actually it's way nicer to just have if be an expression, because otherwise, yeah, you need two different syntaxes, like in Python or C++. Yeah, in Python you put the if in the middle if you want it as an expression. Because Lean is an expression-oriented functional language, there are no conditional statements, only conditional expressions. They are written using if, then, and else. For example, well, if 1 is bigger than 2, then yes, else no. Yeah, and that the value of this whole thing will then just be a string. For the sake of brevity, a series of evaluation steps like this will sometimes be written with arrows between them. Okay, so it's showing here how this expression would be like evaluated inside of the lean compiled program or the interpreter. I don't even know yet if I guess it's a compiled language. For the sake of brevity, a series of evaluation steps like this will sometimes be written with arrows between them. Yeah, so just saying that where this line evaluates to the next line, which evaluates to the next line, and so on. Messages you may meet. Asking Lean to evaluate a function application that is missing an argument will lead to an error message. In particular, the example #eval string.append it is yields a quite long error message. Yeah, let's actually, just for fun, try it out. And could not synthesize a wrapper or toString instance for type string to string. Actually, let's see if it changes anything if we use parentheses. Unexpected token, expected a command. So we cannot use a parentheses here. We have to put a space. Yeah, and then we get the same sort of error. The reason I'm trying this actually is because I was reading about another functional programming language called Coca the other day, and they chose to not follow this like trend in functional programming to just omit the parentheses, but they make it mandatory. And I mean, there are several reasons, like because also of its effect system, but one thing that I found interesting is that apparently having the parentheses be mandatory allows you to provide better error messages in cases like this. So like functional programming languages, especially like Haskell, are kind of notorious for having these like hard to understand error messages. And I guess one part of it is just the types of a lot of functions are just so general that it's hard to give like a good concrete error message. And yeah, apparently the other part is that it's just easier to detect if some argument or something is missing in if you don't have like stuff like currying and leaving out the parentheses. Actually, the language server allows me to go to definition here. That's also really cool. But I mean, for this function seems to be very clear that it takes a string and then another thing, which I don't know what this means, but I guess also some kind of string, and then produces a string. So yeah, I wonder why the error message is this bad. Let's see if the book tells us anything. This message occurs because Lean functions that are applied to only some of their arguments return new functions that are waiting for the rest of the arguments. Yeah, so this is like currying, I guess. So like, don't have Haskell installed here, but I guess you could. Let's actually see. So if we put the parentheses like this, yeah, it actually works because I mean, kind of useless here, but actually like to Lean, this expression here is a function that then only takes one string argument, and so this is like, so we could like, for example, do we could do something like this. Let's see if the syntax is correct. I actually don't want to write it like this. I wanted to have string. Can I write this? Yeah, this actually works. So this is, I think in Haskell it's called currying. So you can partially apply a function. You can just take a function that takes, for example, 2 arguments, only give it 1 argument, and then it gives you another function. Yeah, that's actually, I mean, often it's useful, but I guess it leads to these confusing error messages. Lean cannot display functions to users and thus returns an error when asked to do so. Okay, so now I understand the error. So the error is just saying that, well, it cannot print this function as a string. Exercises. Let's see what they got. What are the values of the following expression? Work them out by hand, then enter them into Lean to check your work. Yeah, so I think these are all fairly obvious. Don't really want to work them out by hand, but let's paste it into Lean. Actually seems interesting that it doesn't care about the white space here. I think Haskell cares more about white space. Maybe I'm wrong. Yeah, 61, ABC, obviously. Yeah, ABC computed in a different way. Yeah, 5 and then not equal. Yeah, okay, so far so good. Next. Types. Types classify programs based on the values that they can compute. Types serve a number of roles in a program. First, they allow the compiler to make decisions about the in-memory representation of a value. Really interesting that they say that as the first point, but yeah, obviously that's one of the the things that really can make statically typed languages kind of more efficient, because the compiler can like exactly use the the representation of the value that exactly like fits the data. So if you have like a C struct versus like a Python class, I mean in Python, as far as I know, you can just like assign new things. I have Python installed. I have, like if I do class A x equals 1 and then A equals A dot x, we have 1. I'm gonna make it a bit bigger, but like this type is sort of I mean, it's not like this will only take like 4 bytes, for example, in memory. Because I mean, Python is kind of like dynamic as a language, so each class you can just create new values on the fly, or new fields on the fly. And also obviously like the variable a itself, I mean, it has to be internally some kind of pointer or something, not just like some simple 4-byte thing on the stack like it would be with a C structure, because I can also now change its type to a string. And I guess like having static types sort of allows you to compile more efficient code in a way. They help programmers to communicate their intent to others, serving as a lightweight specification for the inputs and outputs of a function. The compiler ensures that the program adheres to this specification. Yeah, so that's, I think also, I mean, that's the main thing that many people often talk about. That, well, the first thing is it serves as a way of like documenting what the program does if you like, have a type of each function. And the other thing is that the compiler then also like can do better checks. I guess that's one of the main arguments for having like a strong type system. They prevent various potential mistakes, such as adding a number to a string, and thus reduce the number of tests that are necessary for a program. Yeah, that's obviously another big one in I mean, in Python, if you want to, for example, have a thorough test suite, then it should also include like passing the wrong types and seeing if that sort of breaks in unexpected ways. And obviously in Rust or something, or in Lean, I guess this cannot happen, because the compiler will prevent you from writing such a program. They help the Lean compiler automate the production of auxiliary code that can save boilerplate. So this one is actually not completely clear to me what exactly like that means. I would have to see an example for that. Lean's type system is unusually expressive. Types can encode strong specifications like this sorting function returns a permutation of its input, and flexible specifications like this function has different return types depending on the value of its argument. Actually, that last one I think is also possible in TypeScript. But saying that it returns a permutation of its input, so basically like a sort function, that's like what, it's also the example. I kind of read over that, but obviously like a permutation of the input is just a sorting of, for example, a vector. But that's interesting that this can be like just expressed as a type. The type system can even be used as a full-blown logic for proving mathematical theorems. This cutting-edge expressive power doesn't make simpler types unnecessary, however, and understanding these simpler types is a prerequisite for using the more advanced features. Yeah, let's start simple. Every program in Lean must have a type. In particular, every expression must have a type before it can be evaluated. Actually, I wonder if it has like type inference like Haskell. In the example so far, Lean has been able to discover a type on its own, but it's sometimes necessary to provide one. Obviously it has type inference. We were not specifying types. This is done using the colon operator inside parentheses. Yeah, so the colon here says that this is of type not. Actually, I wonder if they have any other sort of like integer types. I mean, Nat, I would guess, is some kind of big int thing. The natural number starting at 0. Fast arbitrary precision arithmetic library, usually GMP. Yeah, so this is a big integer that will be able to hold arbitrarily many like big numbers. But is there an int? Okay, so there's also an int. What if we write, how can we write power like this? 2 to the power of 32. Int is 63 bits. Interesting. Why not 64? I guess somehow it's, yeah, using that last bit to store some information, but let's see, 63. That still seems to work out, and 64, that also still seems to work out. Interesting. What if we do 128? Why is this working? Why is this working? Can we somehow see the type that it's inferring for this expression? Because I don't see how this can fit into a 64-bit integer. That's, yeah, actually wanna really learn more about this. Let's try something crazy. Yeah, that definitely is. It's kind of switching to the natural number type. That's. I mean, Python does that too. It has like arbitrary precision integers, but if they're like small, it will just, as an optimization, use the platform one. But let's try the same thing in Haskell, if my internet connection will allow us to download Haskell. Let's also install IPython for later. Okay. I think in Haskell it's called also int, so let's see, this is working. 2 to the 64. Oops. Also working. But if I do that as an int, I guess I have to specify it like this. Yeah. So in Haskell, this will give us literally 0, and that's what I would have expected from Lean here. That 2 to the 64, or I guess 63, if they say it's 1 bit less, then would yield 0, but somehow it doesn't. That's interesting. Okay, back to the book. Here nat is the type of natural numbers, which are arbitrary precision unsigned integers. In Lean, nat is the default type for non-negative integer literals. This type is not always the best choice. In C, unsigned integers underflow to the largest representable number when subtraction would otherwise yield a result less than 0. Yeah, so obviously if you like have 0 and you subtract 1, then yeah, you will get a negative number. Let's see if this actually works. Yeah, you get a negative number, and if it's an unsigned integer, actually we don't have unsigned integers here, but then you would get a like the largest positive value because of how 2's complement works. Nat, however, can represent arbitrarily large unsigned numbers so that there is no largest number to underflow to. Thus, subtraction on nat returns 0 when the answer would have otherwise been negative. Okay, so this will give us 0, 1, minus 2. Interesting. Actually, I would rather, have it throw a type error than just returning some obviously wrong result. Evaluates to 0 rather than minus 1. To use a type that can represent the negative integers, provide it directly. 1, minus 2, int. Yeah. With this type, the result is minus 1 as expected. So I guess what if we then do it as a negative? It still works correctly. Really wonder what's going on here. To check the type of an expression without evaluating it, use #check instead of #eval. Yeah, that's also interesting. Okay, so we can know the type without actually doing anything. So I guess we should also be able to do something like check 1 divided by 0 and not get any error because it's gonna be a natural number, even though if we do eval okay, so it just evaluates to 0. That's interesting. In almost every other language, like dividing by 0 would throw some kind of error. I really wonder how this is like going to interact with proofs, because if I accidentally, like Lean is supposed to be used for proving stuff, right? So if I accidentally end up dividing by 0 in a proof, so it's just gonna get me 0 and let me move on. That would be obviously very bad. So yeah, let's read on, see whether there's anything about it. To check the type of an expression before evaluating it. Okay, we already read that. When a program can't be given a type, an error is returned from both #check and #eval. For instance, check string.append, and then we give it a list. Outputs again a very long error message. Type mismatch. Yeah. Okay, but actually very easy to understand. So yeah, we get a list of string, and we expect a single string. So this is actually quite readable. Okay, functions and definitions. In Lean, definitions are introduced using the def keyword. For instance, to determine the name hello, to refer to the string hello, we write def hello and then quotes hello. Yeah, interesting. And yeah, obviously we're leaving out the type here, and somehow it appears to be inferred. In Lean, new names are defined using the colon equal operator, well, colon equal rather than equal sign. Yeah, because obviously the equal sign, like in math, is going to be used to describe equality rather than assignment. That's just how it's used in math. In the definition of hello, the expression hello is simple enough that Lean is able to determine the definition's type automatically. However, most definitions are not so simple, so it will usually be necessary to add a type. This is done using a colon after the name being defined. Yeah, so we already saw that syntax, but actually that's interesting because I think that actually in Haskell it can pretty much always infer the type, even though it's still just like for documentation and readability recommended to always write out the types of your top level definitions. Well, anyway. Now that the names have been defined, they can be used. So #eval, string.append hello, string.append lean, outputs hello lean. Yeah, okay. In Lean, defined names may only be used after their definitions. Yeah, that's also interesting because pretty sure that actually in Haskell it's enough if it's in scope, or at least, well, at least some languages are like that. Like a lot of languages, like in Rust, it doesn't matter if you define a function first, or if you like first define a function that uses it, and then in the same file later you define that function. In many languages, definitions of functions use a different syntax than definitions of other values. For instance, Python function definitions begin with the def keyword, while other definitions are defined with an equal sign. Yeah, and obviously in Lean, functions are just normal values, so we don't really need a different syntax. Okay, so, but there is a distinction. So nonetheless, definitions such as hello introduce names that refer directly to their values rather than zero argument functions that return equivalent results each time they are called. Actually, yeah, then how do you define a zero argument function? Maybe you have to like then explicitly write something like, I guess that unit to nut, for example, like this. So this is how you write lambda expression. So let's see what the type of this is. #check, and then this function, and it gives us something very weird looking. A synthetic hole or synthetic placeholder. Well, this is actually, yeah, because it takes an argument. But if I write it like this, unexpected token. So somehow I cannot write a zero argument function. I guess I could take like unit, and then it will give me this function whose type somehow is, yeah, unit to nut. Interesting. Yeah. So I mean, I guess in Haskell you also cannot do zero argument functions, right? You cannot just yeah, a lambda requires at least one parameter. I mean, obviously in Python, that's not what I wanted. Okay, you can just do a zero argument function. But yeah, interesting that Lean somehow doesn't do that. But I guess, I mean, yeah, what would be the difference anyway, right? You call a function without parentheses, so like syntactically, I guess, like obviously if you just use some value like x, yeah, I mean, how would you even know it's a function? Like, what difference would it even make if it was a function? Defining functions. There are a variety of ways to define functions in Lean. The simplest is to place the function's arguments before the definition's type, separated by spaces. Yeah, so this syntax, I think, to me looks a bit confusing, but functions argument before the definitions type. So this is the function name, then we write the argument, and then we write the type, and then we write the definition. Well, I guess I just find it confusing because there's so many like colons here. Like in Rust, for example, you would like write an arrow right for the return type. Anyway, testing this function with hashtag eval gives 8 as expected. Yeah. But I wonder if we can do this like without actually explicitly naming the argument, like yeah, like currying, I guess. So if we just write it like nut to nut, and then we write +1 like this, unexpected token. Okay, can we write it like this? Unexpected token. Because I'm pretty sure that in Haskell both of these would work. Like I can do +1 as a function and 2. I can also just do plus and 1, 2 as a function application. But so I guess we cannot just use operators as functions here, or at least not like this. Yeah, well, Copilot also just suggests a lambda expression here. Just as functions are applied to multiple arguments by writing spaces between each argument, functions that accept multiple arguments are defined with spaces between the arguments' names and types. Yeah, so multiple arguments just like this. The function maximum, whose result is equal to the greatest of its two arguments, takes two nut arguments n and k and returns a nut. Yeah, obvious. Similarly, the function space between joins two strings with a space between them. So we have one argument before, one argument after the return type here, and yeah. It's interesting that apparently string.append, yeah, I guess only works with two arguments, so we cannot use, cannot just give it a var arg. I wonder if Lean even has like var arg functions that take arbitrarily many arguments. But the thing is that I thought that you can just also do like this syntax here, like the same as Haskell. Wonder why they even use string.append if it has this nice, much nicer looking operator. Yeah. When a defined function like maximum has been provided with its arguments, the result is determined by first replacing the argument names with the provided values in the body, and then evaluating the resulting body. For example, yes, obviously these are gonna be evaluated first, which just follows from the fact that Lean is a strict language. Okay, expressions that evaluate natural numbers, integers, and strings have types that say this. Nut, int, and string respectively. This is also true for functions. A function that accepts a nut and returns a bool has type nut to bool. And a function that accepts two nuts and returns a nut has type nut to nut to nut. Yeah. As a special case, Lean returns a function signature when its name is used directly with #check. Yeah. Entering #check add1 yields the type of add1. However, Lean can be tricked into showing the function's type by writing the function's name in parentheses, which causes the function to be treated as an ordinary expression. Okay, so this, yeah, if you just, let's try this. If we just type it like this, actually, yeah, well, that's because we defined it like that. But if we take the original definition of add1, then this would give us like not just the type but the whole signature including the name. And they're saying if we write parentheses, then what actually is the difference? Let's see. I guess we can we do tuples? Well, yeah, but now it's gonna also use the type. So I guess to see it side by side, you have to look at it one after the other. So yeah, I guess it's just using this different kind of syntax rather than the the other syntax with the arrows. Yeah, interesting. Just as functions are applied to multiple arguments by writing spaces between each argument, functions that accept multiple arguments are defined with spaces between the arguments' names and types. Sorry, we already read that. Yeah, let me get this type. This arrow can also be written with an ASCII alternative arrow, well, with just minus and bigger than. So the preceding types can be written yeah, example, colon, not, and then, yeah, the ASCII arrow. Yeah, yeah, that's nice. Actually, I want to try again how to type actually this arrow. So if we go again and define our not function, yeah, backslash and then 2 is how to type the arrow. So like in LaTeX. Behind the scenes, all functions actually expect precisely one argument. Yeah, that's the currying, I guess. Functions like maximum that seem to take more than one argument are in fact functions that take one argument and then return a new function. Yeah. This new function takes the next argument and the process continues until no more arguments are expected. This can be seen by providing one argument to a multiple argument function. Yeah, already tried that earlier. Yeah, but yeah, then we get just not to not as a type. Using a function that returns a function to implement multiple argument functions is called currying after the mathematician Haskell Curry. Yeah. So in Haskell, the language itself is named after the first name, and then they wanted to include the last name as well, I guess, so they called this kind of feature or this way of function application currying. Function arrows associate to the right, which means that not to not should be parenthesized as, yeah, I mean, that's kind of obvious. So the first argument, you can just supply that, and then you get this function as a result. But yeah, you can obviously leave out the parentheses. Exercises. Define the function join strings with type string to string to string to string that creates a new string by placing its first argument between its second and third argument. Okay, so if we take join string with, well, yeah, we already get it from Copilot. Maybe I should turn that off, but I mean, obvious enough. The definition, just take a separator, string 1, string 2, and concatenate them like this. And yeah, really interesting. It literally like does not allow you to use definitions that come afterwards. So I have to put it like this, and then it works. Yeah. What is the type of join string with and a well, colon and space string? Well, obviously, where it's just gonna be string to string to string, so one one argument removed. Check your answers with lean. Well, obviously the way to check this is with hashtag check, and we get string to string to string. Did I click something? Anyway, define a function volume with type not to not to not to not that computes the volume of a rectangular prism with the given height, width, and depth. Okay, so height, not width, depth. Yeah, I think the correct way is to just multiply them like Copilot suggests, and the type should be 4 times not 1, 2, 3, 4. Yeah, I think we can say that. Defining types. Most type programming languages have some means of defining aliases for types, such as C's typedef. Yeah. In Lean, however, types are a first-class part of the language. They are expressions like any other. And that's really interesting to me, first-class types. This means that definitions can refer to types just as well as they can refer to other values. For example, if string is too much to type, a shorter abbreviation str can be defined. Yeah, so literally with the same syntax we use for values, we can just define this. If we then check str, we can see it's a type, which actually is, yeah, I guess the type of a type is called a kind, at least in Haskell, and I guess you can go like arbitrarily many levels deep, like the type of a type of a type, but it somehow becomes kind of, I don't know about Lean, but in Haskell, it's just like any type is part of this sort of type kind. So it just becomes essentially, if you work at the level of types, it becomes a bit like a dynamically typed language. I think they call this like kind safety as opposed to type safety. Yeah, because for example, what if we check type, and type is type 1? Yeah, so it has this sort of hierarchy. So if we check type 42, Maximum universe level offset threshold. Okay, so you can only go 30 levels deep. So if we check type 21, it gives us type 22. This is this is so interesting. So it, yeah, keeps track of how many levels down the rabbit hole we have gone. Cool. It is then possible to use str as a definitions type instead of string. Yeah, I mean, obviously. The reason this works is that types follow the same rules as the rest of Lean. Types are expressions, and in an expression, a defined name can be replaced with its definition. Because str has been defined to mean string, yeah, it's just gonna be replaced by string here. Yeah, messages you may meet. Okay. Experimenting with using definitions for types is made more complicated by the way that Lean supports overloaded integer literals. If not is too short, a longer name natural number can be defined. Yeah, okay. However, using natural number as a definitions type instead of not does not have the expected effect. In particular, the definition def38 natural number is 38 results in a horrible error message. Failed to synthesize. Of not natural number 38 numerals are polymorphic in Lean, but the numeral 38 cannot be used in a natural number due to the absence of the instance above. Additional diagnostic. That's interesting. Well, if we just do like check 42, it just gives us net as the type. Whereas in Haskell, which also has polymorphic numbers, it gives you that it literally can, like, this is just saying it can be any number. So 42 can be an int, but 42 can also be an integer, which is, I think, Haskell's like big int kind of type, arbitrary precision integer. I think it can even be like a float, yeah. Okay, but so in Lean it somehow like defaults to not, I guess. This error occurs because Lean allows number literals to be overloaded. When it makes sense to do so, natural number literals can be used for new types just as if those types were built into the system. So you can define your own number types, I guess. That's cool. This is part of Lean's mission of making it convenient to represent mathematics, and different branches of mathematics use number notation for very different purposes. The specific feature that allows this overloading does not replace all defined names with their definitions before looking for overloading, which is what leads to the error message above. Okay, I think I need to read that again. Specific feature that allows this overloading does not replace all defined names with their definitions before looking. Okay, I don't understand it. Which is what leads to the error message above. Okay, so it's just saying that this feature is not gonna substitute here not. I wonder why not. One way to work around this limitation is by providing the type not on the right hand side of the definition, causing not's overloading rule to be used for 38. Yeah. The definition is still type correct because natural number is the same as not by definition. Another solution is to define an overloading for natural number that works equivalently to the one for not. This requires more advanced features in Lean, however. Finally, defining the new name for not using abref instead of def allows overloading resolution to replace the defined name with its definition. Definitions written using abref are always unfolded. For instance, abref n type is not. Yes, I think this is the difference between a type alias and a new type, so new type without space between u and type. So I think if you do data my int equals int in Haskell, I guess you have to do like that would be a type, like literally a new type. If you do, how can we do that? If you do, yeah, we can just use it like that, but with my int, that would not work. And I think Go has the most crazy way to do this, because in Go, if you do like type, like it's literally just this one character difference. So this is a alias and this is a new type. It will be treated by the compiler as a different type. Anyway, yeah, so in Lean you use abref, which, yeah, makes more sense as a syntax, I guess. Behind the scenes, some definitions are internally marked as being unfoldable during overload resolution, while others are not. Definitions that are to be unfolded are called reducible. Control over reducibility is essential to allow Lean to scale. Fully unfolding all definitions can result in very large types that are slow for a machine to process and difficult for users to understand. Yeah, I mean, obviously it makes sense because, I mean, if you define your own type, you want the error messages, for example, and the compiler internally to use your type so that, yeah, stuff like errors also then show up with your type rather than the definition of the type. So if it was unfolding everything, yeah, that would also not be good, I guess. Definitions produced with abref are marked as reducible. Structures. The first step in writing programs is usually to identify the problem domain's concept, and then find suitable representations for them in the code. Sometimes a domain concept is a collection of other simpler concepts. In that case, it can be convenient to group these similar concepts together into a single package, which then can be given a meaningful name. In Lean, this is done using structures, which are analogous to structs in C or Rust or records in C#. Defining a structure introduces a completely new type to Lean that can't be reduced to any other type. This is useful because multiple structures might represent different concepts that nonetheless contain the same data. For instance, a point might be represented using either Cartesian or polar coordinates, each being a pair of floating point numbers. Defining separate structures prevents API clients from confusing one for another. Yeah, I mean, this is pretty obvious, I guess. Lean's floating point number type is called float, and IEEE floating point number. Yeah. And floating point numbers are written in the usual notation. Yeah, makes sense. When floating point numbers are written with the decimal point, Lean will infer the type float. If they are written without it, then a type annotation may be necessary. Yeah, also makes sense. A Cartesian product is a structure with two float fields called x and y. This is declared using the structure keyword. Structure point where, yeah, x is a float and y is also a float. And yeah, I guess it has this kind of feature like Rust's derive macro, also deriving in Haskell, that it can just essentially implement an interface. So I guess this is some kind of toString thingy that it automatically implements, like if you do derive display in Rust, I guess. After this declaration point is a new structure type. The final line, which says deriving wrapper, asks Lean to generate code to display values of type point. This is used by #eval to render the results of evaluation for consumption by programmers, analogous to the wrapper function in Python. It is also possible to override the compiler's generated display code. Let's take this definition. The typical way to create a value of a structure is to provide values for all of its fields inside of curly braces. The origin of a Cartesian plane is where x and y are both 0. Yeah, actually I kind of like this syntax. That looks kind of nice. And then if we do eval origin, we will see nothing. No, we will see it here. And I wonder if then can just use dot notation to, yeah, that's actually kind of nice. As far as I understood, like in Haskell, the way to like then you had to write it is like x origin, like that it also becomes a function each field, and they only recently introduced the normal like dot notation. But as far as I know, another thing that you can, for example, do in other languages is do this kind of syntax, that you use it like as a function if you write it with a dot, but seems to not be possible in Lean. Well, guess not a big issue. You can just define a function for it if you really need it. I wonder if there's also a way to like create a new struct with sort of an updated value. Like I don't know how that would work. Like this, for example. Structure instance assigns e to field x, which may be inherited. Yeah, I really wonder whether there's some kind of syntax for that. I guess we will see later in the book. Thank you, Copilot. I guess, yeah, it's like this. Actually, yeah, I like that syntax. That's so easy to read. Like just origin with x equal to 1. Nice, nice. Um, yeah, that's that's really cool syntax actually. Because structures exist to bundle up a collection of data, naming it and treating it as a single unit, it can also be important to be able to extract the individual fields of the structure. Yeah, we already saw how to do that. This can be used to define functions that take structures as arguments. For instance, additions of points is performed by adding the underlying coordinate values. It should be the case that, well, yeah, obviously if you make it like this, then should get this as a result. The function itself takes 2 points as arguments called p1 and p2. The resulting point is based on x and y fields both p1 and p2. Yeah. What I'm wondering if we can do like some kind of desugaring of these, that we don't have to like explicitly name them. Similarly, the distance between 2 points, which is the square root of the sum of the differences in their x and y components, can be written, well, like this, obviously. Pythagorean, or how to say that in English. For example, the distance between 1, 2 and 5 minus 1 is 5. Multiple structures may have different fields with the same name. A three-dimensional point data type may share the fields x, y, and be instantiated with the same field names. This means that the structure's expected type must be known in order to use the curly brace syntax. If the type is not known, Lean will not be able to initiate the structure. Yeah, that makes sense. As usual, the situation can be remedied by providing a type annotation. Yeah, to make programs more concise, Lean also allows the structure type annotation inside the curly braces. Ah, okay. This kind of looks confusing to me, but okay, I guess you can write the point inside. Okay, now we can go to the next part that we already checked how to update them. Imagine a function 0x that replaces the x field of a point with 0. In most programming language communities, this sentence would mean that the memory location pointed to by x was to be overwritten with a new value. However, Lean is a functional programming language. In functional programming communities, what is almost always meant by this kind of statement is that a fresh point is allocated with the x field pointing to the new value, and all other fields pointing to the original value from the input. Yeah, so we have to create a new point object. One way to write 0x is to follow this description literally, filling out the new value for x and manually transferring y. And actually, as far as I know, I read somewhere that Lean uses a functional but in place optimization in the compiler. So I think if the garbage collector can detect that this point, like that there's only one user of this, which is like our current function, then it will actually like update the memory in place, which obviously is a lot more efficient. And I guess some functional programming languages I've heard also have like linear types, so you can even like at compile time have the compiler check that okay, that we are sort of like the owner in the Rust sense of that value, and that we can like modify it in place. Yeah, anyway. This style of programming has drawbacks, however. First off, if a new field is added to a structure, then every site that updates any field at all must be updated, causing maintenance difficulties. Secondly, if the structure contains multiple fields of the same type, then there is a real risk of copy-paste coding leading to field contents being duplicated or switched. Finally, the program becomes long and bureaucratic. Yeah. Lean provides a convenient syntax for replacing some fields in a structure while leaving the others alone. This is done using the with keyword in a structure initialization. The source of unchanged fields occurs before the with, and the new fields occur after. For example, 0x can be written with only the new x value. Yeah, okay, we already saw this syntax. Yeah, I still like it. I think it's actually looks kind of sweet. Remember that this structure update syntax does not modify existing values. It creates new values that share some fields with old values. Given the point 4 and 3, okay, that we are defining here, evaluating it, then evaluating an update of it using 0x, then evaluating it again yields the original value. Yeah, I mean, obviously we don't have mutable state, at least not like observable mutable state. So if if the compiler or the runtime system can deduce that we cannot infer that in-place update, it can still use it as like an internal optimization. Obviously, as the program itself can never see that. One consequence of the fact that structure updates do not modify the original structure is that it becomes easier to reason about cases where the new value is computed from the old one. All reference to the old structure continue to refer to the same field values in all of the new values provided. All reference to the old structure continue to refer to the same field values in all of the new values provided. I think I know what they're saying, but it's kind of phrased a bit confusingly. Behind the scenes, every structure has a constructor. Here the term constructor may be a source of confusion. Unlike constructors in languages such as Java or Python, constructors in Lean are not arbitrary code to be run when a data type is initialized. Yeah, so you cannot just like define a constructor, I guess, that does some like weird computation. Instead, constructors simply gather data to be stored in the newly allocated data structure. It is not possible to provide a custom constructor that pre-processes data or rejects invalid arguments. This is really a case of the word constructor having different but related meanings in the two contexts. By default, the constructor for a structure named S is named s.mk. Here S is a namespace qualifier and mk is the name of the constructor itself. Instead of using curly brace initialization syntax, the constructor can also be applied directly. Yeah. So the thing is, but what happens if I define invalid field name? Yeah, so I cannot use mk as the field name. I don't know why they like abbreviations so much. I mean, just call it make. It's only 2 characters more. Or call it new. It's only 1 character more. However, this is not generally considered to be good Lean style, and Lean even returns its feedback using the standardized structure initializer syntax. Yeah. Constructors have function types, which means they can be used anywhere that a function is expected. Yeah, that's useful. For instance, point.mk is a function that accepts 2 floats and returns a new point. Yeah. To override a structure's constructor name, write it with 2 colons at the beginning. For instance, use point.point instead of point.mk, write okay. To me, that syntax looks a bit confusing because my brain sort of expects something to come after this double colon. But anyway, so I guess we can define it however we want. In addition to the constructor, an accessor function is defined for each field of a structure. These have the same name as the field in the data structure's namespace. Ah, okay, so this is how you access it. So you go point.x derived from origin. So this is how you get the x out of it again. Interesting. I guess it makes more sense because in this kind of thing that can you even type this without having to type? I guess you need some sort of type extension or whatever for that. In Haskell it's kind of like then, as far as I read, I'm not really again using Haskell, but sort of read a bit about it on the internet, and apparently this is then sort of like duck type, that this kind of function will then get the x out of any structure that has a field named x. And here I guess we have explicitly a function that takes a point and not anything with a field that has an x or some crazy thing like that. Okay. In fact, just as the curly braced structure construction syntax, it is converted to a call to the structure's constructor behind the scenes. The syntax x in the prior definition of add points is converted into the call to the x accessor. That is #eval origin.x and #eval .x.origin both yield. Yeah, I mean, obviously behind the scenes this is gonna be the same like code. Accessor dot notation is usable with more than just structure fields. It can also be used for functions that take any number of arguments. Okay, more generally, accessor notation has the form target.f, arg1, arg2, and so on. If target has type t, then the function named t.f is called. And t then is, I guess, some kind of namespace in this context. Target becomes its leftmost argument of type t, which is often but not always the first one. How can it be not the first one? And arg1, arg2 are provided in order as the remaining arguments. For instance, string.append can be invoked from a string with accessor notation, even though string is not a structure with an append field. Yeah, pretty sure that this is also how the dot notation works in Rust in the background, or at least somehow similar to that. But yeah, I mean, yeah, that's cool, I guess. In that example, targets represent one string and arg1 represents another. The function point.modifyBoth, that is modifyBoth defined in the point namespace, applies a function to both fields in a point. Point.modifyBoth. So we can just define a function like in the point namespace, but outside of the struct itself. So that really seems to me similar to Rust. So if you do, and then you do something like this, and then like outside of the structure definition itself, you can define like a function that will then be callable with the dot syntax on point. Interesting. Okay. Even though the point argument comes after the function argument, it can be used with dot notation as well. And that's definitely, I think, different from Rust or other languages that I've seen. That with the dot notation, it doesn't have to be the first one. So it just, yeah, I wonder how, I guess it's just using then the first one that has the type that's equal to the namespace. That's a really interesting feature. Okay, interesting. Exercises. Define a structure named rectangular prism that contains the height, width, and depth of a rectangular prism, each as a float. Okay. I guess we want here float, and yeah, also, so I guess this is a bit like the, what's it even called in Haskell, like the offside rule or something, that it sort of then just takes everything that's at the same indentation level here, the next indentation level, to be part of this definition. So I guess if I do this, it's gonna give me an error. But if I indent it further, it's not gonna give me an error. Interesting. Deriving wrapper. Define a function named volume rectangular prism to float that computes the volume of a rectangular prism. Yeah, so but we can do that as with this syntax, like rectangular prism dot volume, yeah, and then do it like this. But I really wonder if we can pattern match on this. Like instead of writing p, we write height, width, and depth, and then just doing it like this. Unexpected token, but somehow this is not. Yeah, this seems to be not possible, I guess, or maybe there's a different syntax for this kind of like pattern matching or destructuring. Okay, define a structure named segment that represents a line segment by its endpoints, and define a function length segment to float that computes the length of a line segment. Segment should have at most 2 fields. Well, yeah, so where we just do, I guess we cannot use end. I'll just do p1 and p2. Yeah, just using the other point definition that we have. Which names are introduced by the declaration of rectangular prism? Well, sometimes I wish they had solutions for these. I don't know if there are solutions anywhere, but obviously the name of the type itself, and then everything that's in that namespace. So rectangular prism dot height dot width and dot depth. And I guess this will also introduce some kind of function. I don't know what it's gonna be called, but I guess wrapper prec, whatever. That yeah, that's gonna be defined in that rectangular prism namespace as well, I assume. Actually, I wonder if we can call this. Let's define one, and well, first of all, prism1 dot volume. That seems to work. And then, how was it called? Wrapper prec? No. Somehow we cannot call this. So I guess it doesn't work like this. So maybe wrapper prec prism1 could not sensitize a wrapper to string for a type not std. And I guess then we have to provide this with a number, and that maybe that's the width for it to be displayed. That actually, yeah, I'm getting into a total different rabbit hole here. Honestly, I don't know if what that number is. Maybe it's the indentation. Doesn't seem to make a difference in the output here. But anyway, so 1, 2, 3, 4, and for this 5, I guess 5 different names would be my answer that it's introducing. Which names are introduced by the following declarations of hamster and book? What are their types? Okay, let's just do hamster. So we forgot one. The rectangular prism.mk, like the constructor itself, is also introduced. Okay, so we introduce hamster itself as a type. We introduce hamster.mk as a constructor. We introduce hamster.name and hamster.fluffy as functions that go from like hamster to string and hamster to bool. And obviously hamster.mk would be string to bool to hamster. Seems clear enough. Data types and patterns. Structures enable multiple independent pieces of data to be combined into a coherent whole, sorry for my English, that is represented by a brand new type. Types such as structures that group together a collection of values are called product types. Yeah, that's because they are like, mathematically speaking, like the Cartesian product. So if you imagine that like f64 is a set, right, that contains all f64 values. Then let's imagine this is the Cartesian like product. Then a point is like an element of this kind of set, like a tuple of one f64 and another f64, and I think that's why they're called product types. Many domain concepts, however, can't be naturally represented as structures. For instance, an application might need to track user permissions, where some users are document owners, some may edit documents, and others may only read them. A calculator has a number of binary operators such as addition, subtraction, and multiplication. Structures do not provide an easy way to encode multiple choices. Yeah, and that's why we need algebraic data types, I guess. Similarly, while a structure is an excellent way to keep track of a fixed set of fields, many applications require data that may contain an arbitrary number of elements. Most classic data structures, such as trees and lists, have a recursive structure where the tail of a list is itself a list, or where the left and right branches of a binary tree are themselves binary trees. In the aforementioned calculator, the structure of expressions themselves is recursive. The summands in an addition expression may themselves be multiplication expressions, for instance. Data types that allow choices are called sum types, and data types that can include instances of themselves are called recursive data types. Yeah, so for the sum types, so like I guess our point is like this, right? So it's a product, mathematically speaking, a Cartesian product, and a sum type would then be something like, can I type this? So that contains either one float or one string. So it sort of is this, mathematically speaking, this sort of disjoint union, which is kind of like a sum, because the size of the set will be the size of the set float plus the size of the set string. Recursive sum types are called inductive data types. Okay, That sounds like an educated word. Recursive sum types are called inductive data types because mathematical induction may be used to prove statements about them. Okay, yeah. Yeah, I mean, I guess that makes sense. If you want to prove anything about, for example, a tree, then the tool of choice would be an inductive proof. When programming, inductive data types are consumed through pattern matching and recursive functions. Many of the built-in types are actually inductive data types in the standard library. Yeah, for instance, bool is an inductive data type. Yes, that's such like an ivory tower name, I guess. But so yeah, bool has, I guess, two constructors that are zero argument, and those are the only two values. So I guess it's a sum type. And I guess in Lean we write that using inductive instead of like just like in in Rust where you would write it just like as an enum, but basically it just means, I guess, an enum. This definition has two main parts. The first line provides the name of the new type bool, while the remaining lines each describe a constructor. As with constructors of structures, constructors of inductive data types are mere inert receivers and containers for other data rather than places to insert arbitrary initialization and validation code. Unlike structures, inductive data types may have multiple constructors. Yeah, I mean, we can see two here. Here there are two constructors, true and false, and neither take any arguments. Just as a structure declaration places its names in a namespace named after the declared type, an inductive data type places the names of its constructors in a namespace. In the Lean standard library, true and false are re-exported from this namespace that they can be written alone rather than as bool.true and bool.false. So if we do check false, we should get bool.false. Yeah. I wonder if we can like redefine this or if it will give us some kind of error. Yeah, it will give us an error, but if I do bool2, then that works. Nice. From a data modeling perspective, inductive data types are used in many of the same contexts where a sealed abstract class might be used in other languages. Languages like C# or Java, one might write a similar definition of bool as, well, there's abstract class, there's two kind of subclasses. Yeah, honestly, I find like object-oriented programming like this quite confusing. Like I would rather have something like Rust style enums, or I guess these inductive types in Lean. Anyway, however, these specifics of these representations are fairly different. Yeah, obviously. In particular, each non-abstract class creates both a new type and a new ways of allocating data. In the object-oriented example, true and false are both types that are more specific than bool, while Lean definitions introduces only the new type bool. Yeah, because in this case, true is also a type, not only bool. So it's not like true is of type bool, but I guess each instance of true is also an instance of bool. And also in Java, then you could create multiple instances of true. And to actually make this work, you would have to like override the equals method, because otherwise you could have two different values for true that are not equal. The type not of non-negative integers is an inductive data type. So this is using like the what's it called, piano axioms or something. Yeah, piano axioms, I guess, for defining integers. Let's see. Check 0. No, it's not re-exported, so we have to do not.0, which is a value, but then what's the difference with 0 not, which will give us here a different representation. But what if we do eval? It will just give us 0. So yeah, I mean, I would guess that inside of the compiler they have some optimization for this, because that would be like super inefficient to represent natural numbers like this. But for inductive proofs, I guess it's useful to have this sort of definition, because you can, I guess, like destructure it and like go back to the previous natural number and then relate that to like the stuff you already proved about smaller numbers. Here 0 represents 0, while suc represents the successor of some other number. The nut mentioned in suc's declaration is the very type nut that is in the process of being defined. Successor means one greater than, so the successor of 5 is 6, and the successor of, well, I'm not going to read that. Using this definition, 4 is represented as, yeah, nut.suc of nut.suc of nut.suc of nut.suc of nut.suc of 0. Let's actually see if we can evaluate that. I guess that's going to work. Yeah, that's going to give us 4, but I want to know then we should also be able to do 0.suc.suc.suc. I guess we are not. Well, if it should just do 1. And that's interesting, but I guess if we do, maybe we have to declare it as a nut. Yeah, and then we can write a super efficient unary representation of 4. Yeah, using this nice dot syntax. This definition is almost like the definition of bool with slightly different names. Well, I mean, not really, because in bool we didn't have this sort of data. The only real difference is that suc is followed by n of nut, which specifies that the constructor suc takes an argument of type nut, which happens to be named n. The names 0 and suc are in a namespace named after their types, so they must be referred to as nut.0 and nut.suc. Argument names such as n may occur in Lean's error messages and in feedback provided when writing mathematical proofs. Lean also has an optional syntax for providing arguments by name. That's actually really cool. Yeah, that's something I wish more languages had. Generally, however, the choice of argument name is less important than the choice of structure field name, as it does not form as large a part of the API. But I guess that means you cannot just rename an argument, because you will break API compatibility if you can specify the name in the call side. Okay, we have a C# or Java example. Abstract class nut, class 0 is nut, class suc, yeah. Which again is really not the same as in Lean here, because 0 is a separate type and suc is a separate like object type, whereas here it's a function. And at the same time, well, it constructs a nut and it doesn't construct a suc, and here it constructs a suc, which is also a nut, this function. Just as in the bool example above, this defines more types than the Lean equivalent. Yeah, that's what I said. Additionally, this example highlights how Lean data type constructors are much more like subclasses of an abstract class than they are like constructors in C# or Java, as the constructor shown here contains initialization code to be executed. Yeah, this is not something that's going to be happening in Lean, I guess. Some types are also similar to using a string tag to encode discriminated unions in TypeScript. In TypeScript, nut could be defined as follows. Interface 0 is tag 0, interface suc is, yeah, it's a discriminated union. You can also do that in C, but well, I've always found it ugly. Like, I know why like TypeScript is, I guess, doing that, because it's like just supposed to be the superset of JavaScript, but as a syntax, I really don't think this is very concise or very nice. Also because at runtime it's then going to be represented using this actual field tag that they all gonna have, these objects, whereas in Rust, at least if you define an enum, the compiler can make often a very efficient representation out of that. Just like C# and Java, this encoding ends up with more types than in Lean, because 0 and suc are each a type on their own. It also illustrates that Lean constructors correspond to objects in JavaScript or TypeScript that include a tag that identifies the contents. Pattern matching. Let's see how they handle pattern matching. In many languages, these kinds of data are consumed by first using an instance of operator to check which subclass has been received, and then reading the value of the fields that are available in the given subclass. The instance of check determines which code to run, ensuring that the data needed by this code is available while the fields themselves provide the data. In Lean, both of these purposes are simultaneously served by pattern matching. Yeah, just like Rust or Haskell, I guess. Or most functional languages. An example of a function that uses pattern matching is 0, which is a function that returns true when its argument is not .0 or false otherwise. I mean, this is really maybe not a good example because you could define this just in a way simpler fashion, but yeah, we match n with not .0, so we can pattern match against the constructor that was used to like create the object that we're dealing with here. And if it is constructed with a 0, then, well, obviously it's 0. The match expression is provided in the function's argument n for destructuring. The match expression is provided in the function's argument n for destructuring. Yeah. Okay, I get it. If n was constructed by not.0, then the first branch of the pattern match is taken, and if the result is true. If n was constructed by not.suck, then the second branch is taken and the result is false. Step-by-step evaluation of is0, not.0 produces, well, yeah, just go through and then evaluate this branch. Evaluation of is05 proceeds similarly. Yeah, we get this huge unary representation of 5, which I'm pretty sure it's not actually gonna be represented like that at runtime. Yeah, and then we go to the false branch. The k in the second branch of the pattern is0 is not decorative. It marks that the not is an argument to the not.suck visible with the provided name. Yeah. But I guess we could just write an underscore or something here because we're not actually using that name. The smaller number can then be used to compute the final result of the expression. Just as the successor of some number n is greater than n, that is n plus 1, the predecessor of a number is 1 less than it. If pred is a function that finds the predecessor of not, then it should be the case that the following example find the expected result. Yes, obviously. Because not cannot represent negative numbers, not.0 is a bit of a conundrum, so I guess they just define it that the predecessor of 0 is 0. I would define it that it throws an error. To find the predecessor of not, the first step is to check which constructor was used to create it. Yeah. If it was not.0, then the result is 0. If it was suck, then yeah, it's just k. That is easy enough. We're just destructuring it and yeah, taking the data out, which is the data inside of the successor is by definition the predecessor. Pattern matching can be used with structures as well as with sumtypes. For instance, a function that extracts a third dimension from a point 3D can be written as follows. Okay, and that's how we can destructure structures. And I wonder if we have to provide this sort of alias here or if that is actually optional. Let's try this out. Did I define a point 3D? No. So first we need to define a structure point 3D. The language server actually tells us that this is, I guess, useless. And in fact, we can, we don't have to provide the alias. And in fact, can we leave this out? Can we just write it set? Can we write like this? No, we cannot. With 2 dots. So similar to Rust, I guess. This is really, nice. So we can, I think in Rust you can do this directly inside of the argument. So you could like directly write this here and then write set. But I guess this is not in fact allowed. Maybe if we surround it with another pair of parentheses. Nope, I guess lean does not allow this. Well, I guess the syntax is more obvious anyway, but takes 2 extra lines. In this case, it would have been much simpler to just use, obviously, point3d.set accessor, but structure patterns are occasionally the simplest way to write a function. Recursive functions. Yeah. Definitions that refer to the name being defined are called recursive definitions. Inductive data types are allowed to be recursive indeed. Not is an example of such a data type because suck demands another not. Yeah, recursive data types can represent arbitrarily large data, limited only by technical factors like available memory. Just as it would be impossible to write down one constructor for each natural number in the data type definition, is it also impossible to write down a pattern match case for each possibility, obviously. Recursive data types are nicely complemented by recursive functions. Simple recursive function over nut checks whether its argument is even. In this case, nut.0 is even. Yeah. Non-recursive branches of the code like this one are called base cases. The successor of an odd number is even and the successor of an even number is odd. This means that the number built with nut.suck is even if and only if its argument is not even. Yeah, actually this is, yeah, I guess a really simple way to define an even function without using like the modulus operator or something else, but yeah, that seems simple enough, and it's recursive because it calls itself, but it's really inefficient, I guess, because it always has to walk back up to the base case. So let me see if I can select this. So if I take this even function here, wonder why my computer appears to be so slow right now. What's taking? Well, anyway, it doesn't appear to use that many resources, but somehow it's sluggish, or at least VS Code. I blame Lean. Restart file. Doesn't make it better. Okay, what if we eval even of 2 to the power of 64? I guess we have to use. And we get obviously a stack overflow, yeah. Because I guess this is not tail recursive, so it will use a new stack frame each time, which is kind of, yeah. Yeah, I mean, you could rewrite this to be like be tail recursive, but yeah. So obviously this is really the most inefficient way you could think to write like an even function. But I guess it's just for learning here. This pattern of thought is typical for writing recursive functions on NUT. First, identify what to do for nut.0, then determine how to transform a result for an arbitrary nut into the result for its successor and apply this transformation to the result of the recursive call. This pattern is called structural recursion. Yeah, I guess if you were writing a proof, then it would literally just be structural induction. Unlike many languages, Lean ensures by default that every recursive function will eventually reach a base case. Interesting. So I cannot do like def, for example, like this. Well, that's not even what I wanted to write, but this is what Copilot suggests. But anyway, this is a, well, this is not a function, I guess. This is just a value, but it's infinitely recursive because there's never a base case. And this would actually be allowed in Haskell, but obviously if it's a strict language, you cannot what do you call it? You cannot evaluate that. Fail to show termination, but this error message again it tells you that it's trying to analyze it for termination, so it's a kind of a totality checker. And obviously it's because of the halting problem, it should be impossible to write a perfect totality checker. So I guess there's gonna be cases where it has false, what is it, false positives or false negatives? Where it's going to have false positive, false negatives, I guess, where it thinks that it doesn't terminate, but it will in fact terminate. Yeah, because obviously if it could like determine termination of arbitrary expressions, then we would have solved the halting problem, which is not possible. From a programmer's perspective, this rules out accidental infinite loops, but this feature is especially important when proving theorems where infinite loops cause major difficulties. A consequence of this is that Lean will not accept a version of even that attempts to invoke itself recursively on the original number. Yeah, that's cool. The important part of the error message is that Lean could not determine the recursive function always reaches a base case, because it doesn't. Yeah. Even though addition takes 2 arguments, only one of them needs to be inspected. To add 0 to a number n, just return n. To add the successor of k to n, take the successor of the result of adding k. I think here they mean n minus 1. Def plus nk. Yeah, we're matching k. successor k prime, it's like adding n to k prime, so k minus 1, when taking the successor of that. Again, the most inefficient way you could add two numbers. In the definition of plus, the name k prime is chosen to indicate that it is connected to but not identical with the argument k. For instance, walking through the evaluation of 3 plus 2 yields the following steps. Yeah, we're gonna reduce the second argument until it eventually reaches 0, plus 3, 0, and then, yeah, we're just gonna return 3 and then gonna go back up, back down the stack. So we're gonna build up this huge stack of function calls until we reach 0 in the second argument and then go down again, which is really inefficient. One way to think about addition is that n plus k applies not.suck k times to n. Similarly, multiplication n times k adds n itself k times and subtracts n minus k takes n's predecessor k times. Yeah, this actually is not going to be correct because it's just going to give us like, well, obviously not cannot have negative numbers. So let's define pred as well and try to eval minus 5, 3, which, oops, we need to restart the lean server. And I guess my infinite list, I deleted it, yeah. Which is gonna give us 2, but if we take 10 here, it's just gonna give us 0. And what I also wonder is, in Haskell, you can like write this inline using this syntax. I guess Lean doesn't have that, because sometimes it makes it a lot more readable to write a function like inline like this, like an infix notation instead of prefix. But yeah, anyway. Not every function can be easily written using structural recursion. The understanding of addition as iterated not.suck multiplication, as iterated addition, and subtraction as iterated predecessor suggests an implementation of division as iterated subtraction. In this case, if the numerator is less than the divisor, the result is 0, otherwise the result is the successor of dividing the numerator minus the divisor by the divisor. Okay, that sounds really confusing if you spell it out like that, but essentially, well, we just we're literally just counting how many, like how you would do it maybe in your head, how many times we can fit k into n. Somehow they're saying this will not work. As long as the second argument is not 0, this program terminates, as it always makes progress towards the base case. However, it is not structurally recursive because it doesn't follow the pattern of finding a result for 0 and transforming a result for a smaller nut into a result for its successor. In particular, the recursive invocation of the function is applied to the result of another function call rather than to an input constructor's arguments. Thus, Lean rejects it with the following message: failed to show termination for diff with errors, failed to infer structural recursion. Not considering parameter k of diff, it is unchanged in the recursive calls. Yeah, because obviously we cannot divide by 0. This message means that diff requires a manual proof of termination. So that's actually cool. So I guess if the compiler itself cannot show the termination, which obviously because of the halting problem it cannot always do, then we can provide a manual proof for it. That's actually a really interesting feature. Okay, but I guess we cannot really try this out right now because failed to show termination. I wonder if we can failed to show termination. Well, what if we do, how do we write a comment even? Like with this. Right, Copilot at least won't show us the how to show the termination, or maybe it will. Well, what I was really just wondering is, so I guess use this termination by syntax. Yeah, I was wondering if we can just trick it into like evaluating now by using this sorry thing, which apparently can prove everything in Lean. But I really don't know enough about it yet to figure this one out. So let's just go to the next one, polymorphism. Another nice word. Just as in most languages, types in Lean can take arguments. For instance, a type list not describes a list of natural numbers. List string describes a list of strings, and list point describes a list of points. This is very similar to, well, the Java notation, or most, I guess, C++-like languages notation for this kind of thing. Just as Lean uses space to pass arguments to a function, it uses a space to pass arguments to a type. Yeah, that's just the consequential thing to do. In functional programming, the term polymorphism typically refers to data types and definitions that take types as arguments. Yeah, so there's two types of polymorphism, right? So there's the sort of parametric polymorphism, which is exactly this kind of thing, list of natural numbers, because you're parameterizing a type by another type. And then the term polymorphism, sometimes it's also used for something else, which is ad hoc polymorphism, which essentially is just dynamic dispatch, a different name for dynamic dispatch. For example, in Haskell, if I do 1 plus 0 plus 1 plus 0, obviously, or 1 plus 1, I'm using the same symbol here, which is like a plus function. I mean, in this case, probably provided by the compiler, but the same principle applies for your own like traits, or I guess type classes in Haskell. So you can have it like infer which function to use depending on the types. So this add function here is gonna resolve to some machine instruction that will add floating point numbers, and this one is gonna resolve to some machine instruction that will add ints, I guess. So that's also, I guess, polymorphism. At least some people also call that polymorphism. Anyway, this is different from the object-oriented programming community, where the term typically refers to subclasses that may override some behaviors of their superclass. Yeah, I guess that's what I meant by the ad hoc polymorphism, because yeah, it's at runtime, or like at least maybe not at runtime, but based on the type, it then determines which method to call. In this book, polymorphism is always used to refer to the first sense of the word. These type arguments can be used in the data type or definition, which allows the same data type or definition to be used with any type that results from replacing the argument's names with some other types. Well, I guess this is not very complicated, that's just generics. The point structure requires that both x and y fields are floats. There is, however, nothing about points that requires a specific representation for each coordinate. A polymorphic version of point called pPoint can take a type as an argument and then use that type for both fields. Yeah, so we have this pPoint structure, which takes an alpha, which is a type, and then we have x and y, which are then gonna be of alpha. And I wonder, what makes me really curious right now is how we can derive wrapper here, even though we did not provide a constraint that the type alpha needs to also implement wrapper. Because I could do like eval pPoint, I guess x. Let's do a let's do it like this and define this as a pPoint of nut to nut unexpected token. Maybe I have to wrap this in parentheses, or what was the syntax again? I have to use the assignment syntax here. Now it's giving me an error. Invalid notation, expected type is not known. So essentially what I want to try out, what if I create a structure with something that is not representable as a string and then try to like print that, but I guess it really doesn't want me to do this like this. What if I do like .mk? And again, my computer is really sluggish. Maybe it's because of the recording or something, even though we didn't see much CPU being used earlier. This is crazy slow. Maybe it's because of Lean 4 running in the background. So here we have written some bullshit. Stuck at solving universe constraint. Maybe it's because the type is so weird. So if we make it to take unit, Could not synthesize, yeah, that's what I'm wondering. Could not synthesize wrapper or toString instance for type because, yeah. So somehow this deriving macro is, I guess, smart enough to, because this is now a valid point, a point that contains two functions, but it somehow was smart enough to like insert some constraint that alpha needs to also be, yeah, wrapper. Interesting. Just as function definitions arguments are written immediately after the name being defined, a structure's arguments are written immediately after the structure's name. Yeah. It is customary to use Greek letters to name type arguments in Lean when no more specific name suggests itself. Type is a type that describes other types, so not list, string, and ppoint, int all have the type. Yeah, I think it's kind of confusing to use type here. So I say, yeah, I mean, you can find more. You can also use the word like kind, so the kind of point int, I guess, is type. But, well, then what you do after one level, so I guess you can also just say the type of the type. Just like list, ppoint can be used by providing a specific type as its argument. Yeah, ppoint not, and yeah, easy enough. In this example, both fields are expected to be nuts. Just as a function is called by replacing its argument variables with its argument values, providing ppoint with the type nut as an argument yields a structure in which the fields x and y have the type nut because the argument name alpha has been replaced by the argument type nut. Well, yeah. Somehow this book kind of uses really long paragraphs to describe really obvious things sometimes, but yeah, types are ordinary expressions in Lean, so passing arguments to polymorphic types like ppoint doesn't require any special syntax. Yeah. Definitions may also take types as arguments, which makes them polymorphic. The function replaceX replaces the x field of a point with a new value. In order to allow replaceX to work with any polymorphic point, it must be polymorphic itself. This is achieved by having its first argument be the type of the point's fields, with later arguments referring back to the first argument's name. So we have this replace x. First it takes a type, and that I think to me is a bit confusing that there's literally no separation here, that because the first argument and a second argument are very different things, very different domains. So the first one is well, literally a type and the second one is a value. But I guess that in Lean types are also just values, and I also guess that you don't have to specify this explicitly, so I guess it will be inferred. And what I'm wondering now is if the order is like if the type has to come first or if this is just like a convention. So what if we take this type and first of all it didn't even give me an error, so if I leave it out, automatically inserted implicit parameters. It implicitly inserts it. And what if I insert it at the end? Then it suddenly gives me a very weird error, so I guess it has to come first. In other words, when the types of the arguments point and ux mention alpha, they are referring to whichever type was provided as the first argument. This is similar to the way that function argument names refer to the values that were provided when they occur in the function's body. This can be seen by asking Lean to check the type of replace x and then asking it to check the type of replace x not. Well, yeah, replace x is obviously going to just give us the same signature back and replace x. What if we give it something like meaningless, like say type? Then it detects that type is not of type. But somehow it still gives us something which is sorry. And what if we take a value? Then obviously also not going to work. And what if we take, well, if we take ppoint, I guess this function maybe that should, ppoint itself is polymorphic, so then yeah, let's take just normal point. That should actually work. Yeah, we have a point of points. This function type includes the name of the first argument, and later arguments in the type refer back to this name. Yeah. Okay, well that's also why it has to come first, because later you can refer to it here. I guess. Just as the value of a function application is found by replacing the argument name with the provided argument value in the function's body, the type of a function application is found by replacing the argument's name with the provided value in the function's return type. Providing the first argument not causes all occurrence of alpha in the remainder of the type to be replaced with not. Yeah, easy enough. Because the remaining arguments are not explicitly named, no further substitution occurs as more arguments are provided. Yeah. So I guess, yeah, the type doesn't change dramatically, it just removes one error here. The fact that the type of the whole function application expression was determined by passing a type as an argument has no bearing on the ability to evaluate it. Yeah, that's nice. Polymorphic functions work by taking a named type argument and having later types refer to the argument's name. I don't know if it's just me, but somehow the way they describe it makes it sound more complicated than it is. However, there's nothing special about type arguments that allows them to be named. Given a data type that represents positive or negative signs, inductive sign, where positive, negative, it is possible to write a function whose argument is a sign. If the argument is positive, the function returns not, while if it's negative, it returns an int. So this is really crazy to me that we can use a match statement here on the type level with actually exactly the same syntax. So we have here this, after this colon, we have the return type, and the return type itself is a expression that is evaluated based on the type of the first, or not even the type, the value of the first argument. So based on the value, this type changes. That's crazy. Because types are first class and can be computed using ordinary rules of the Lean language, they can be computed by pattern matching against a data type. When Lean is checking this function, it uses the fact that the match expression in the function's body corresponds to the match expression in the type to make not be the expected type for the pos case and to make int for the expected type for the neg case. Applying pos or neg to pos results in the argument name s in the body function the argument name s in the body of the function and its return type being replaced by pos. Evaluation can occur both in the expression and its type. Yeah, crazy. Linked lists. Lean standard library includes a canonical linked list data type called list and special syntax that makes it more convenient to use. Lists are written in square brackets. For instance, a list that contains the prime numbers less than 10 can be written using, well, primes under 10, like that. Behind the scenes list is an inductive data type defined like this. So yeah, with nil and cons, like you always do it in functional programming. What I'm really wondering is if they in the compiler really allocate like a special heap allocation, a separate heap allocation for each cons, or if there's some compiler optimization going on here that represents, for example, this list where it like knows the length as one single allocation. Well, anyway, the actual definition in the standard library is slightly different because it uses features that have not been presented, but it is substantially similar. This definition says that list takes a single type as its argument, just as ppoint did. This type is the type of the entry stored in the list. According to the constructor, a list alpha can be built with either nil or cons. The constructor nil represents empty lists and the constructor cons is used for non-empty lists. The first argument to cons is the head of the list and the second argument is the tail. A list that contains n entries contains n cons constructors, the last of which has nil as its tail. Yeah, this is obvious enough and we can like explicitly spell out this list using the cons constructors. These two definitions are completely equivalent, but primes under 10 is much easier to read. Yeah, obviously. Functions that consume lists can be defined in the same way as functions that consume nuts. Indeed, one way to think of A list is as a nut that has an extra data field dangling off of each sub-constructor. From this point of view, computing the length of a list is the process of replacing each cons with a sub and the final nil with 0. Just as replace x took the type of the fields of the point as an argument, length takes the type of the list's entries. For example, if the list contains strings, then the first argument is string.length. For example, if the list contains string, then the first argument is string length. String sourdough bread should be computed like this. Okay, so the first argument is the type of the list, but I guess we can infer that as well. And just will replace, as they said, each cons with a suck call. The definition of length is both polymorphic because it takes the list entry type as an argument and recursive because it refers to itself. Generally, functions follow the shape of the data. Recursive data types lead to recursive functions and polymorphic data types lead to polymorphic functions. Yeah, you can see the definition here, easy enough. In the cons case we have y and y's and we ignore the y and we compute it here and they actually pass the type manually here. Names such as x's and y's are conventionally used to stand for lists of unknown values. The s in the name indicates that they are plural, so they are pronounced x's and y's rather than xs and ys. To make it easier to read functions on lists, the bracket notation can be used to pattern match against nil, and infix : can be used in place of cons. Yeah, that's a bit like Haskell. Implicit arguments. Both replace x and length are somewhat bureaucratic to use because the type argument is typically uniquely determined by the later values. Indeed, in most languages, the compiler is perfectly capable of determining the type argument on its own and only occasionally needs help from users. This is also the case in Lean. Arguments can be declared implicitly by wrapping them in curly braces instead of parentheses when defining a function. For example, a version of replace x with an implicit type argument looks like this. So I guess there's separate syntax for using type inference. So I guess we have to use these different braces for if we want to infer it. Yeah. Can be used with NUT origin without providing NUT explicitly because Lean can infer the value of alpha from the later arguments. Nice. Similarly, length, can do the same. In the standard library, Lean calls this function list.length, which means that dot syntax that is used for structure field access can be used to find the length of a list. It's actually interesting because we get like the similar syntax to, for example, JavaScript or Java, but for totally different reasons, because here it's actually really just calling a function, whereas in, for example, Java, then it's more like a field access because the length is explicitly like stored in memory together with an array. Just as in C# and Java require type arguments to be provided explicitly from time to time, Lean is not always capable of finding implicit arguments. In these cases, they can be provided using their names. For example, a version list.length that only works for lists of integers can be specified by setting alpha to int. And then you use this different syntax with, I guess, the assignment operator. And you cannot just, because it's an inferred argument, I guess you cannot just use it like normally, just passing int itself. And what would happen if you do that? Yeah, we get application type mismatch because it's not a list. More built-in data types. In addition to lists, Lean standard library contains a number of other structures and inductive data types that can be used in a variety of contexts. Option, well, this is probably gonna be like maybe in Haskell or like option in Rust. Not every list has a first entry. Some lists are empty. Many operations on collections may fail to find what they are looking for. For instance, a function that finds the first entry in a list may not find any such entry. It must therefore have a way to signal that there was no first entry. Many languages have a null value that represents the absence of a value. That's actually the $1 billion mistake, I guess, null pointers. Instead of equipping existing types with a special null value, Lean provides a data type called option that equips some other data type with an indicator for missing values. That's a much more sensible way. For instance, a nullable int is represented by an option int, and a nullable list of strings is represented by option of list of string. Introducing a new type to represent nullability means that the type system ensures that checks for null cannot be forgotten, because option int cannot be used in contexts where int is expected. Option has two constructors called sum and none that represent the non-null and the null versions of the underlying type. Yeah, that seems easy enough. The option type is very similar to nullable types in languages like C# and Kotlin, but it is not identical. In these languages, if a type, say Boolean, always refers to actual values of the type true and false, type Boolean question mark or nullable Boolean additionally admits the null value. Tracking this in the type system is very useful. The type checker and other tooling can help programmers remember to check for null, and APIs that explicitly describe nullabilities through type signatures are more informative than other ones that don't. However, these nullable types differ from Lean's option in one important way, which is that they don't allow multiple layers of optionality. While you can have an option of an int. Kotlin, on the other hand, treats t question mark as being equivalent to t question mark. This subtle difference is rarely relevant in practice, but it can matter from time to time. Okay, well, I didn't know that. That's actually interesting and makes no sense to me. Why would they do that? But to find the first entry in a list, if it exists, use list.head question mark. The question mark is part of the name and is not related to the use of a question mark to indicate nullable types in C# or Kotlin. In the definition of list.head question mark, an underscore is used to represent the tail of the list. Well, yeah, underscore can match anything, but do not introduce variable names. Yeah, that makes sense. A Lean naming convention is to define operations that might fail in groups using the suffixes question mark for a version that returns an option, exclamation mark for a version that crashes when provided with invalid input, and D for a version that returns a default value when the operation would otherwise fail. Yeah, so I guess there's list.head question mark, head exclamation mark, and head D, which will give you the way to specify default value, which is weird to me that you need a special version for that, because usually the option type itself has a way to like get or default, like if it's none then return a default value kind of function. So that seems to kind of redundant that we need head D, but yeah. The question mark and exclamation mark are part of the name, not special syntax, as Lean's naming rules are more liberal than many languages. Yeah. Because head question mark is defined in the list namespace, it can be used with accessor notation. Yeah. So I guess if you have a list of lists, you could use .head. We cannot use it on an empty list, but not because it's empty, but because it doesn't know the type. Okay. So in this output, the m dot like some number represents a type that it couldn't find. So this is like a type hole, I guess, and well, obviously this nil itself is like polymorphic. So like in Haskell it would just be something like this, that can be any type alpha for all alpha. But I guess, well, what if I do check nil in Lean, where it just gives me again this type hole kind of thing. Yeah. These unknown parts are called meta variables, and they occur in some error messages. In order to evaluate an expression, Lean needs to be able to find its type, and the type was unavailable because the empty list does not have any entries from which the type can be found. Yeah, so if we actually just give the type explicitly, then it works as expected. The error messages provide a useful clue. Both messages use the same meta variable to describe the missing implicit argument, which means that Lean determined that the two missing pieces will share a solution even though it was unable to determine the actual value. Yeah, so we can see here it's the same number. Prot. The prod structure, short for product, is a generic way of joining two values together. For instance, a prod nut string contains a nut and a string. In other words, p-point nut could be replaced by prod nut nut. Prod is very much like C#'s tuples, the pair or triple types in Kotlin, and tuple in C++. Many applications are best served by defining their own structures, even for simple cases like point, because using domain terminology can make it easier to read the code. Additionally, defining structure types helps catch more errors by assigning different types to different domain concepts, preventing them from being mixed up. On the other hand, there are some cases where it is not worth the overhead of defining a new type. Additionally, some libraries are sufficiently generic that there is no more specific concept than a pair. Finally, the standard library contains a variety of convenience functions that make it easier to work with the built-in pair type. Yeah, so prod is just a tuple of two arguments, I guess. I wonder how you do arbitrary tuples. Lists are used so frequently that there is special syntax to make them more readable. For the same reason, both the product type and its constructor have a special syntax. The type prod alpha beta is typically written as alpha Cartesian product beta, mirroring the usual notation for the Cartesian product of sets. Similarly, the usual mathematical notation for pairs is available for prod. In other words, instead of writing it like with this convoluted way, you can just write it as a normal tuple. Both notations are right associative. Okay, so we can just leave out the parentheses and then get a pair of pairs somehow. So what if I do like .snd, then we get this kind of tuple, and .snd again we get the third element. Yeah. In other words, all products of more than two types and their corresponding constructors are actually nested products and nested pairs behind the scenes. Interesting. Sum. The sum data type is a generic way of allocating a choice between values of different types, so like a disjoint union. For instance, sum string int is either a string or an int. Like prod sum should be used either when writing very generic code or for a very small section of code where there is no sensible domain specific type, or when the standard library contains useful functions. In most situations, it is more readable and maintainable to use a custom inductive data type. Variables of type sum alpha beta are either the constructor in L applied to a value of type alpha or in R. That's a very weird names. Very weird name. In left injection and right injection. Just as the Cartesian product notation for prod, a circle plus notation is used for sum. Yeah. So that we can also do something like yeah, we can in fact apparently use the same type, so it doesn't need to be yeah, different data types. As an example, if pet names can either be dog names or cat names, then a type for them can be introduced as a sum of strings. Yeah, totally not contrived. In a real program, it would usually be better to define a custom inductive data type for this purpose with informative constructor names. Here, sum.in L can be used for dog names and sum.in R can be used for cat names. The constructors can be used to write a list of animal names. Yeah. Pattern matching can be used to distinguish between the two constructors. For instance, a function that counts the number of dogs in a list of animal names, that is the number of sum.inl. The number of sum.inl constructors looks like this. Yeah, well, you pattern match on them, and yeah, just add one if there's a inl constructor. Unit. So unit is a type that only has one value. Unit is a type that with just one argumentless constructor called unit. In other words, it describes only a single value, which consists of said constructor applied to no arguments whatsoever. Unit is defined as follows. Yeah, just like that. And I guess it also has a special syntax. On its own, unit is not particularly useful. However, in polymorphic code, it can be used as a placeholder for data that is missing. For instance, the following inductive data type represents arithmetic expressions. Yeah, honestly, the syntax is confusing me right now. So int, we have this a and n type and then an arrow and then int, and then arithmetic expression. Yeah, so I guess we just explicitly give it a first argument here that then has to be a type, and the expression is then also of that type. And plus obviously can take two expressions and yields a third expression, and same for minus and times. The type argument a and n stands for annotation, and each constructor is annotated. Expressions coming from a parser might be annotated with source locations. So a return type of arith export source pos ensures that the parser puts source pos at each sub-expression. Expressions that don't come from the parser, however, will not have source location. Yeah, so we can give unit as an placeholder. Additionally, because all Lean functions have arguments, zero-argument functions in other languages can be represented as functions that take a unit argument. In a return position, the unit type is similar to void in languages derived from C. In the C family, a function that returns void will return control to its caller, but it will not return any interesting value. By being intentionally uninteresting value, unit allows this to be expressed without requiring a special purpose void feature in the type system. Unit's constructor can be written as empty parentheses. Yeah, so it's like an empty tuple. Empty, well, that's then just a data type that has no constructors. Thus it indicates unreachable code, because no series of calls can ever terminate with a value or type empty. Empty is not used nearly as often as unit, however it is useful in some specialized contexts. Many polymorphic data types do not use all of their type arguments in their constructors. For instance, sum.inl and sum.inr each use one of sum's type arguments. Using empty as one of the type arguments to sum can rule out one of the constructors at a particular point in a program. Yeah. Naming sums, products, and units. Generally speaking, types that offer multiple constructors are called sum types, while types whose single constructor takes multiple arguments are called product types. These terms are related to sums and products used in ordinary arithmetic. The relationship is easiest to see when the types involved contain a finite number of values. If alpha and beta are types that contain n and k distinct values respectively, then, well, alpha sum beta contains n plus k distinct values, and alpha times beta contains n times k distinct values. For instance, bool has two values and unit has one value. The product bool times unit has, well, two values, and bool plus unit has three values. Yeah. Messages you may meet. Not all definable structures or inductive types can have the type. In particular, if a constructor takes an arbitrary type as an argument, then the inductive type must have a different type, because it's kind of like a function from type to type. These errors usually state something about universe levels. For example, for this inductive type, my type of type, where the constructor takes a type and a value and returns my type, this has invalid universe level. Later chapter describes why this is the case and how to modify definitions to make them work. For now, try making the type argument to the inductive type as a whole rather than to the constructor. Yeah. Similarly, if a constructor's argument is a function that takes the data type being defined as an argument, then the definition is rejected. Non-positive occurrence of the data type being declared. For technical reasons, allowing these data types could make it possible to undermine Lean's internal logic, making it unsuitable for use as a theorem prover. Recursive functions that take two parameters should not match against the pair, but rather match each parameter independently. Otherwise, the mechanism in Lean that checks whether recursive calls are made on smaller values is unable to see the connection between the input value and the argument in the recursive call. That's interesting, so we cannot match on pairs like that. Otherwise, yeah, we have our halting problem again, that it cannot prove that it will halt. So we have to write this really ugly thing here, I guess, or there's a way around it. Yeah. Forgetting an argument to an inductive type can also yield a confusing message. For example, when the argument alpha is not passed to my type in Cedar's type, Lean replies with the following error. yeah, my type here should be an alpha in the end, and type expected got, well, yeah, that's essentially a function from type to type, because we need to provide it a type alpha, and then it gives us a type, my type of alpha. Yeah, the same message can appear when type arguments are omitted in other contexts. Yeah, that seems easy enough. Exercises. Write a function to find the last entry in a list. It should return an option. Okay, let's see. Well, let's see what Copilot seems to be doing something that's rather reasonable. Alpha, we have a list alpha, we return an option. Let's see if this is correct. We match L, empty list gives us none. List with one element, well, obviously gives us that element, and if we have more than one, then we just recursively go down the list. And obviously the order, I guess, here is important, because if you would put this first before the other one, then it wouldn't work. Yeah, let's try it out. Works. Write a function that finds the first entry in a list that satisfies a given predicate. Start the definition with find first. Okay. Yeah. I mean, I have done this kind of stuff in Haskell as well. Bit too lazy to type it out all the time, but let's see what the AI did. Yeah, it literally just recurses down the list, and if our predicate returns true, then we just give that value. Otherwise, yeah, we go down the tail. Write a function prod.switch that switches the two fields in a pair for each other. That should be trivial, right? We should literally be able to pattern match with this like syntactic sugar here. Match, yeah, literally like AB goes to BA. Unexpected, I forgot def, yeah. Rewrite the pet name example to use a custom data type and compare it to the version that uses some, well, pet name, it was a sum type, I guess. So we would have to define it as inductive pet name where, yeah, but not like that pet name where we get, why is everything so slow right now? We want to have a string like this. I think this is how you would do it. Write a function zip that combines two lists into a list of pairs. The resulting list should be as long as the shortest input list. Yeah. And the thing is that here I guess we cannot match directly on pairs, or can we? I mean, this is what Copilot suggests, and that's also what I would have written. And somehow it actually works. We don't need to in fact nest them like we saw earlier. So if either of them is empty, we just return the empty list, and otherwise we take the first one of both and take that as the head, and oops, that's not what I wanted. Please go away. Yeah, that seems easy enough. Write a polymorphic function take that returns the first n in a list where n is not. If the list contains fewer than n entries, then the resulting list should be the entire input list. Yeah. So we have to like, did they give us the type? No, they didn't give us the type. Def take, so first we have an alpha type and n not in the list, so it gave us the correct thing here, I think. For 0 we just return the empty list, or if the list is empty, return the empty list. And this is really interesting. It allows us to do pattern matching like on like I guess this is syntactic sugar for the suck constructor. Didn't know that's possible. Yeah, that should work. Yeah. Using the analogy between types and arithmetic, write a function that distributes products over sums. Using the analogy between types and arithmetic, write a function that distributes products over sums. It should have a type alpha times, well, the sum of beta and gamma goes to alpha times beta plus alpha times gamma. That's a bit more interesting. Okay, so first I need to define the types, obviously. Can I can I do? Just apparently we can define multiple types at once. And I guess we need parentheses here instead of, I think I'm going to try restarting VS Code. This is so slow. Yeah, much better. We get this to this unexpected token. I guess we need to type a name for this thing and the name for, no, this is the return type, so it should be after the colon. So sorry. Let's see, does this even give the correct thing? We get, yeah, alpha times beta plus gamma is giving us alpha times beta plus alpha times gamma. So I guess we need to match X. Let's see, this is the alpha, we are matching with A, and then either we can get inductive left or inductive right. And if we're in the left case, we need to give this alpha and beta, otherwise alpha and gamma. So if we try to eval this, then obviously it cannot evaluate it because we're not giving it the type beta. So we would need to give it something for beta, I guess. Okay, this is the first one that is really confusing me. That's not a field of structure prod. What if I tried with type inference, like, can I not do the type like that? Do I need parentheses? Implicit argument gamma. Why? I have string, and here string, here I have float, so it should be able to tell that gamma is float. That is how you specify the type, right? We had, do I need another set of parentheses? That's crazy. Okay, I need another set of parentheses, but so I'm giving it a tuple of a and a sum type with an integer, and then it gives me the sum, the left part of the sum type with a and the integer. And I guess if I do in R, it would give it to me with a float. Yeah, not confusing at all. Using the analogy between types and arithmetic, write a function that turns multiplication by 2 into a sum. In other words, it should have type bool times alpha multiplication by 2 into a sum. Bool times alpha goes to alpha plus alpha. Don't really know what they mean here. So I guess if it's true, it should go to the first one. If it's false, it should go to the second one or something like that. But I don't know why it says multiplication by 2. Because bool has 2 constructors, I guess. So we're essentially converting from a tagged union, or like a, yeah, I guess this is literally how you could represent a tagged union to a sum type. Okay. And that's literally what also Copilot is suggesting, I guess. No, it's not. This makes no sense. We want to have, what's the type we want? We want a bool. We want a bool. And we want a, actually we don't want a beta here. Just want a bool and alpha. The other way around, a alpha. And that should give us a alpha. No, how you write it? O plus alpha. Yeah, that's, yeah, I guess that's what they mean. Next chapter, additional conveniences. I really wonder if table of contents. I don't see the solutions here, so maybe it doesn't have solutions. Who knows? Lean contains a number of convenience features that make programs much more concise. Automatic implicit parameters. When writing polymorphic functions in Lean, it is typically not necessary to list all the implicit parameters. Instead, they can simply be mentioned. If Lean can determine their type, then they are automatically inserted as implicit parameters. In other words, the previous definition of length can be written without the alpha, so it will literally know that alpha is an arbitrary type. Interesting. Yeah, obviously that's simpler to write. Pattern matching definitions. When defining functions with def, it's quite common to name an argument and then immediately use it with pattern matching. Yeah, that was also what I thought. For instance, in length, the number x's is used only in match. In these situations, the cases of the match expression can be written directly without naming the argument at all. Okay, well, I guess that only works if you match on the first argument. The first step is to move the argument types to the right of the colon. Okay, so we have to write the list alpha not here, but yeah, on the right of the colon. Then replace dot colon equals with each case of the pattern match. Okay, so we don't have the colon equals syntax here, we directly start with the pipe. Interesting, but yeah, that's more concise. This syntax can also be used to define functions that take more than one argument. In this case, their patterns are separated by commas. Yeah, so I guess that's similar to what we were doing here, except we were doing it explicitly, but I wonder why this is possible when earlier they told us that we cannot match like this. Yeah. Guess if you write the parentheses, then it cannot determine the termination, but if you leave them out, then it can. That's weird. For instance, drop takes a number n and the list and returns the list after removing the first n entries. Yeah, easy enough. With this syntax, it looks really a lot cleaner. Named arguments and patterns can also be used in the same definition. For instance, a function that takes a default value and an optional value and returns the default when the optional value is none can be written as from option default alpha. So I guess because this is before the parentheses, we are not matching before the colon, we are not matching on the default here, but we are matching on the option. Yeah, option.getD. So literally to do like the same as this headD function that they had, we could do this, or apparently this one exists, so that I guess it makes it a little bit shorter. But I really don't see why they're defining an extra function here just to save these really few characters. Local definitions. It is often useful to name intermediate steps in a computation. In many cases, intermediate values represent useful concepts all on their own, and naming them explicitly can make the program easier to read. Yeah, definitely. In other cases, the intermediate value is used more than once. As in most other languages, writing down the same code twice in Lean causes it to be computed twice, while saving the result in a variable leads to the result of the computation being saved and reused. For instance, unzip is a function that transforms a list of pairs into a pair of lists. When the list of pairs is empty, then the result of unzip is a pair of empty lists. When the list of pairs has a pair at its head, then the two fields of the pair are added to the result of unzipping the rest of the list. Okay, I don't get this. When the list of pairs has a pair at its head, then the two fields of the pair are added to the result of unzipping the rest of the list. Yeah. And this is something again that's easier to read in code than in words, I guess. Yeah, and here we're uselessly computing unzip twice. Unfortunately, there's a problem. This code is slower than it needs to be. Each entry in the list of pairs leads to two recursive calls, which makes this function take exponential time. However, both recursive calls will have the same result, so there is no reason to make the recursive call twice. In Lean, the result of the recursive call can be named and thus saved using let. Local definitions with let resemble top-level definitions with def. It takes a name to be locally defined, arguments, if desired, a type, signature, and then a body following colon equal. After a local definition, the expression in which the local definition is available, called the body of the let expression, must be on a new line starting at a column in the file that is less than or equal to that of the let keyword. Let unzip, yeah, we call unzip, and then in the body here we can use the unzipped definition. Simple enough. Local definitions of let may also use pattern matching when one pattern is enough to match all cases of a data type. In the case of unzip, the result of the recursive call is a pair, because pairs have only a single constructor, the named unzipped can be replaced with a pair pattern. So directly in let we can destructure it. That's also interesting and convenient. Judicious use of patterns with let can make code easier to read compared to writing the accessor calls by hand. Yeah. The biggest difference between let and def is that recursive let definitions must explicitly be indicated by writing let rec. For instance, one way to reverse a list involves a recursive helper function as in this definition. Yeah, so because this helper function, I guess, is recursive, it calls itself, we need to use let rec. Wonder why we need a special syntax, but I guess they have their reasons. Yeah, the reverse works by just putting everything from like the left hand argument into the right hand argument, and that causes it to be reversed. Yeah. The helper function walks down the input list, moving one entry at a time over to so far. When it reaches the end of the input list, so far contains a reversed version of the input. Type inference. In many situations, Lean can automatically determine an expression's type. In these cases, explicit types may be omitted from both top-level definitions with def and local definitions with let. For example, the recursive call to unzip does not need an annotation. Yeah, so it can just infer the type. So rule of thumb, omitting the types of literal values like strings and numbers usually works, although Lean may pick a type for literal numbers that is more specific than the intended type. Lean can usually determine a type for a function application because it already knows the argument types and the return type. Omitting return types for function definitions will often work, but function parameters typically require annotations. Definitions that are not functions like unzipped in the example do not need type annotations in their bodies if their bodies do not need type annotations and the body of this definition is a function application. Yeah, guess you just guess the general rule, at least in Haskell, was always to just provide type definitions for your top level definitions, and internal stuff can usually be inferred. Yeah. And here, even on the top level, it's literally omitting the return type. Yeah, generally speaking, it is a good idea to err on the side of too many rather than too few type annotations. First off, explicit types communicate assumptions about the code to readers. Even if Lean can determine a type on its own, it can still be easy to read code without having to repeatedly query Lean for type information. Secondly, explicit types help localize errors. The more explicit a program is about its types, the more informative the error messages can be. This is especially important in a language like Lean that has a very expressive type system. Thirdly, explicit types make it easier to write the program in the first place. A type is a specification, and the compiler's feedback can be a helpful tool in writing a program that meets the specification. Finally, Lean's type inference is a best effort system. Because Lean's type system is so expressive, there is no best or most general type to find for all expressions. That's interesting. So I thought, well, I guess it's because it's such a powerful type system. Because if you have like a normal, like Hindley Milner, I think it's called, style type system, I think it's actually always possible to find the most general type, but I guess in Lean it's not. This means that if you get a type, there's no guarantee that it's the right type for a given application. Yeah, I mean 14 can be not or int. Missing type annotations can give confusing error messages. Yeah, that's very confusing. This pattern contains meta variables, even though I guess it doesn't look like it. This is because match needs to know the type of the value being inspected, but that type was not available. A meta variable is an unknown part of a program. Yeah, that's the one with m.anumber. They are described in the section on polymorphism. Yeah, we saw that. Even some very simple programs require type annotations. For instance, the identity function just returns whatever argument is passed. With arguments and type annotations, it looks like that. Def ID, we get an X, which is an alpha, and value is an alpha. Lean is capable of determining the return type on its own, so we can just specify the type of the function, but omitting the argument type, however, causes an error failed to infer binder type, which, yeah, is confusing to me. Why can it not just determine that X is an arbitrary type, but yeah, I guess it cannot. Simultaneous matching. Pattern matching expressions, just like pattern matching definitions, can match on multiple values at once. Both the expression to be inspected and the pattern that they match against are written with commas between them. Similarly to the syntax used for definitions, here's a version of drop. Yeah, that's what I discovered earlier, that we can do that. Simultaneous matching resembles matching on a pair, but there's an important difference. Lean tracks the connection between the expression being matched and the patterns, and this information is used for purposes that include checking for termination and propagating static type information. As a result, the version of same length that matches a pair is rejected by the termination checker because the connection between X's and the pattern X colon colon X's is obscured by the intervening pair. Yeah, because there's a pair constructor here, apparently then it cannot track it anymore. And we get this determination error. Natural number patterns. In the section on data types and patterns, even was defined like this. And yeah, just like I saw in the code that Copilot suggested earlier, we can also write n+1 for nut.suck, yeah, which looks a lot nicer, to be honest. In this notation, the arguments to the plus pattern serve different roles. Behind the scenes, the left argument, n above, becomes an argument to some number of nut.suck patterns, and the right argument, 1 above, determines how many nut.suck to wrap around the pattern. The explicit pattern in half, which divides a nut by 2 and drops the remainder. Yeah, we can write it literally as n.2 instead of having to write this ugly thing with 2 suck constructors. That's definitely nice. When using the syntax to the second argument to plus should always be a literal nut, even though addition is commutative. Flipping the argument in a pattern can result in errors. Yeah, because it's not really addition, it's syntactic sugar for destructuring a nut constructor. This instruction enables Lean to transform all uses of the plus notation in a pattern into uses of the underlying nut.suck, keeping the language simpler behind the scenes. Anonymous functions. Yeah, lambda expressions basically. Functions in Lean need not be defined at the top level. As expressions, functions are produced with the fun syntax. Yeah, a very fun syntax. Function expressions begin with the keyword fun, followed by one or more parameters which are separated from the return expression using this type of error. For instance, a function that adds 1 to a number can be written like this. Fun x maps to x plus 1. Yeah, we can then write also type annotations for these, and we can also make them generic. Interesting. This style of anonymous function expression is often referred to as lambda expression because the typical notation used in mathematical descriptions of programming languages uses the Greek letter lambda, where Lean has the keyword fun. Even though Lean does permit a lambda to be used instead of fun, it is most common to write fun. Yeah, I guess it's just more fun that way. Anonymous functions also support the multiple pattern style used in def. Okay, that's cool. So we can like directly pattern match, and we don't even have to name the argument in that case. Just gives us sort of this, yeah, implicitly named argument here. Interesting. Note that Lean's own description of the function has a named argument and a match expression. Many of Lean's convenient syntactic shorthands are expanded to simpler syntax behind the scenes, and the abstraction sometimes leaks. Definitions using def that take arguments may be rewritten as function expressions. Yeah, so this is just like, don't know what you call that. I think it has a name in lambda calculus, like eta reduction or something like that. But yeah, this obviously is the same as the other double definition without the fun here. When an anonymous function is very simple, like fun x maps to x plus 1, the syntax for creating the function can be fairly verbose. In that particular example, 6 non-whitespace characters are used to introduce the function, and its body consists only of 3 non-whitespace characters. For these simple cases, Lean provides a shorthand in an expression surrounded by parentheses, a centered dot character can stand for a parameter and the expression inside the parentheses becomes the function's body. Okay, so we can write this kind of +1 function like that. If we do eval, we get 6. Interesting. And we write this, I guess, using c dot. I guess not. How do we write this? Dot? No. Wanna know how to type this. The center dot always creates a function out of the closest surrounding set of parentheses. So this is a function that returns a pair of numbers. Is a pair of a function and a number. Yeah. This really makes sense. I just wonder how we can type this center dot or just slash dot. Well, that's so easy. Yeah. Namespaces. Each name in Lean occurs in a namespace, which is a collection of names. Names are placed in namespaces using dot, so list.map is the name map in the list namespace. Names in different namespaces do not conflict with each other. Yeah, that's like the point of namespaces. Namespaces may be nested. Yeah. Names can be directly defined within a namespace. Yeah. Because nut is also the name of a type. Dot notation is available to call nut.double. Yeah. In addition to defining names directly in a namespace, a sequence of declarations can be placed in a namespace using the namespace and end commands. Yeah. Okay. That's also easy enough. Everything up to the end. I wonder why sometimes they use end and sometimes they use indentation. So I would have expected that we just do namespace and then indent everything that's supposed to be in there, but I guess here they opted to go for the end syntax. To refer to them, prefix their names with new namespace, well, dot. Yeah, namespaces may be opened, which allows the names in them to be used without explicit qualification. Writing open my namespace in before an expression causes the content of my namespace to be available in the expression. Yeah, that's useful, as it's like using namespace in C++, or yeah, a bit like an import statement, I guess, in Haskell or something, maybe, or like a use statement in Rust. Namespaces can also be opened prior to a command. Yeah, okay, so we can use it with something like #check. Function signatures show the name's full namespace. Namespaces may additionally be opened for all following commands for the rest of the file. To do this, simply omit the in, yeah, just in the top level to open if let. I wonder if this is like Rust's if let. When consuming values that have a sum type, it is often the case that only a single constructor is of interest. For example, given this type that represents a subset of markdown inline elements, well, line break string and emphasis, a function that recognizes string elements and extracts their contents can be written like this: inline.string s, yeah, checks whether it's a inline.string. And here we can use if let with a pattern, and if it matches that pattern, we go to the then branch, otherwise to the none. Very useful. Yeah, it's like a let, but we can provide a fallback. Positional structure arguments. The section on structures presents two ways of constructing structures, where with the constructor with the brace notation. In some contexts, it can be convenient to pass arguments positionally rather than by name, but without naming the constructor directly. For instance, defining a variety of similar structure types can help keep domain concepts separate, but the natural way to read the code may treat each of them as being essentially a tuple. In these contexts, the argument can be enclosed in angle bracket. A point can be written as, yeah, so be careful, even though they look like a less than sign, greater than sign, these are angle brackets. Yeah, we have to type them with this syntax. Just as with the brace notation for named constructor arguments, this positional syntax can only be used in a context where Lean can determine the structure's type. Yeah, so we should be able to eval 1, 2. If we specify that it is a point, and apparently we need these parentheses, and then we get a point here. Very nice shorthand. syntax, I guess. String interpolation. In Lean, prefixing a string with S exclamation mark triggers interpolation, where the expression contained in curly braces inside the string are replaced with their values, similar to F strings in Python. Yeah, S exclamation mark. We can write something in there. Let's try it. S exclamation. What if we write something that cannot be? Failed to synthesize to string type. But if we do point.mk12, failed to synthesize. Guess we can also not do that, but if we do, well, we can define it like, I guess we have to put the type here, and then like this, and it still doesn't work. Even though we have, I guess we need deriving to string or something. If that can even be derived, I guess cannot. So need to do something that. But what if we define it as not like this? Then it works. Yeah, interesting. Yeah, this is because there's no standard way to convert functions into strings. The Lean compiler maintains a table that describes how to convert values of various types into strings, and the message failed to synthesize instance means that the Lean compiler didn't find an entry in this table for the given type. This uses the same language feature as the deriving wrapper syntax. Yeah, want to really know how the like trait system or type class system works. Let's go to the summary, evaluating expressions. Well, yeah, we saw that Lean is expression based and that we don't have mutable state. Functions, yeah, they're first class values, that they're curried by default, so that literally they only take one argument. And yeah, if they take more than one, then basically it's a function that first takes the first argument, then returns a function, and then the returned function kind of consumes the second argument. We can do lambda expressions using fun. We can use the center dot to provide shorthand lambda expressions, and we can define them using def or using let. Let, I guess, being for internal definitions. Types. Every expression needs to have a type. Yeah. Types can be, well, arbitrarily complex, like algebraic data types. Lean's types can also express arbitrary mathematics. That's really, I guess, the part that makes it interesting as a theorem prover. Like other languages, types in Lean can express lightweight specifications for programs that are checked by the Lean compiler, obviating the need for certain classes of unit tests. But we cannot just do simple cases. We can provide arbitrary mathematics, unifying the worlds of programming and theorem proving. That sounds really exciting. While using Lean for proving theorems is mostly out of scope for this book. Yeah, we have another book. Maybe I will read it at some point when I have time. Some expressions can be given multiple types. Yeah. We have type inference, but maybe it's better to write types out explicitly on the top level. Yeah, we can have polymorphic types, so types that are parameterized by types, and these use basically like, yeah, just the same syntax as passing normal arguments. Structures and inductive types, well, structure is like a product type, inductive is like a sum type. Yeah, and they are differentiated by their names, so even if they have like identical fields and values, they're considered to be different. So it's not structural typing, it has some name in programming language theory, I forgot. Yeah, constructors are not like in the object-oriented sense constructors. Yeah, we get these accessor functions for free, and we can consume them with pattern matching, and we can do recursion. Like in other languages, we can just call a function from itself. And Lean, unlike other languages, has this sort of totality checker that, yeah, it needs to be able to prove that we are actually making in some way the argument smaller. And I guess we have learned that if it cannot prove that, there's a way to manually specify a proof, but we haven't yet seen how. Yeah, I wonder if you can write non-terminating functions at all in Lean, because some functions, like for example, if you want to write a REPL that like takes an expression and prints it, that's something that's not going to terminate, but I guess we're going to be able to write that like using IO monad or something like that. Okay, in the next chapter, Hello World, and I think this is a good place to end the video. Maybe I will, or hopefully I will. Hopefully I will have time at some point to also record one for the second chapter.